Thank you for being here today, all our attendees. There are people also in the room. We have our SP Northeast section helping us to get connection today. Please, thank you very much. I really appreciate it. We have connected from different nationalities, and on behalf of the International Energy Agency, the Technology Collaboration Program, and Enhanced Oil Recovery Group, we would like to say thank you to all of you for being here today, for be trusting on us to continue doing these webinars options as we have been working on improve and get the liaison into the EOR. With that, I would like to say thank you all of you. Let me see if you are seeing the current presentation, please. Thank you very much. On behalf of the Enhanced Oil Recovery TCP, again, thank you. Good morning, good afternoon, good evening. Sabal Her, Mesar Nor, bonjour, bon dia. Good morning, everyone. Good afternoon, good evening. Thank you for being here connected today. We will be working on the different aspects. We have it connections. We are going to present to you what is going to be our next steps. We are having here together from the International Energy Agency coming into the different opportunities, working together, how we are going to be part as well of the solution. Our oil and gas industry is providing energy, and it's going to be providing continuous energy for our society. So how we are going to articulate it with another TCPs, how we are going to articulate our technology is something that from the Enhanced Oil Recovery Group, we are working on. The maturity from our technologies have been something that we have been discussed before. And we really would like to put together how we are going to bring up these embryonic technologies, emerging technologies, and mature technologies together to increase the barrels. Today, our assets and mature fields believe on us, believe in our EOR technologies to increase the production and to provide the energy we're going to do. So that's why we would like to give our support to these embryonic technologies and to understand as well the different portfolio that we have on technology that can come together on this race of technology that we should put into the energy transition, into the carbonization system and energy efficiency processes. Different countries around the world today working on enhanced oil recovery, on EOR. And on this EOR process, we have been learned from all the different countries related to microbial, catalytic, in-situ reactions, upgrading, high pressure injection, miscible foam, dilution, hybrid systems, immiscible foam, seawater surfactants, alkali surfactants, low salinity, and there are more reactions and actions that we have been working on. Understand ourselves and be together and share the knowledge is something that we really would like to have and be together on it. So the invitation is to be part. If your country are still not part of the TCP, Technology Collaboration Program, please drop me an email. I will write into the chat my email or contact our mailing contact that you haven't received for the invitation today. Your details. Welcome to be part of the International Energy Agency Technology Collaboration Program. From the countries we have on 2015, we start to continue growing and we like to involve more countries around the world. These countries we really would like to encourage and to interchange more knowledge. Actually, I would like to say thank you to all our volunteers that we have today. And if you want to be volunteers in some of the technology collaborations task force we have today, please welcome to do it. Today, I would like to recognize Liz Balbuena. I would like to recognize Sol Reyes, Adriana Castro, Maria Rosa Cardona, and the support of SP Northeast, that without their help, this cannot be possible. they have been contacting you, we have been recording, we have been working on, and in contact with all of that, we will proceed to continue doing as well. Not only to do and to deploy a webinar, we would like to deploy reports, we would like to deploy high quality documents from the International Energy Agency on EOR. And I invite you to be part of these changes and new time we are working on. All of this because our main guidelines come together with this framework, with these options that we have today, that our principles are to do this coordination and planning framework on research, on shared activities, do participation with a special interest on what are the needs we have in our projects, exchange information, exchange scientists, technicians, experts, that as we are here today, thank you all the different doctors, masters, and students that we have here, and people involved on the EOR projects, because we together, we can encourage and continue doing this effort on EOR, bringing as part of the solution. So the TCP is going to be your board and as well your option that we can support you to continue doing. Insitu reactions is something that we should care about it. How we are going to connect our oil and gas assets with EOR TCP principles is something that we should continue connected, and how we are going to connect this one to more reactions, not only the reactions we have on the surface, on surface too. In the surface, depends on the different method we are applying, is something that we should care about. We should look at our emulsions, we should look at our water management, we should look at our reservoir productivity, and how we can continue to encourage this on the framework of efficiently manner that we need to understand and put in place as well natural solutions, emissions control, circular economy, renewables energy, energy efficiency, CCUS, hydrogen perspective, geothermal perspectives, all this one. If we understand and we put the different reactions from the different processes, we can start to interconnect what we are going to have in our surface conditions, and different states of our EOR. The invitation is to do that. The invitation is to be part of what we are doing today, and we are going to be continue doing our efforts. I would like to invite you to come into our worldwide event. It's going to be held normally it's on presence in Australia, should be this year, but we are today due to the pandemic doing virtually. So we will be connected. We will send you the invitation as well. Every country of the International Energy Agency are going to be presented as well. Paper from that one, and we will continue with the webinar series under the different task force. Different task forces are related to what we have been working today in our different sections. The TCP has these sections related to studies of fluids interface porous media, surfactants and polymer, thermal recovery, gas flooding, dynamic reservoir, emerging technologies. Task forces are related to it, and we are working on that with the volunteers group that some of them have been connected here today. We will continue on that, and we will provide. We'd like to say thank you to all of you that have been already connected in our microbial EOR that happened on the 29th of May, quite close a month ago, where we bring this journey, and you encourage us to become and to continue doing the quality on this one. And actually, I invite you to continue participating in our webinars for our future editions. With that, I would like to present today our agenda that we are going to be working on in situ reactions from our work that we have been working today. Really appreciate your time, really appreciate what you are doing here today, all of you connected at this time. We have intervention from Austria, China, India, Kuwait. We have from USA, Brazil, different hemispheres connected, and Colombia. Thank you very much, really appreciate it. On behalf of the executive committee, we would like to say thank you, and we leave open our Insitu reactions webinars today. Thank you, Liz. Thank you, Adriana. Thank you, Sol, Maria Rosa, again, for an amazing job, and all the panelists, all the speakers, and we will be here in the journey. Please feel free to put your questions into the chat, and we will start now with our meeting. Thank you very much.
Our next presentation will be developed by Gisela Vanega Cavas. She leads the Integrated Services team of OMB E&P Development. Gisela joined OMB in July 2018 in the New Technology Department, where she worked on alkali polymer fluids, carbonates EOR, and developing and implementing OMB machine learning workflow for uncertainty management. She holds a master's degree in reservoir systems from Colorado School of Mines, a petroleum engineer bachelor degree, and a diploma in hydrogeology. Gisela will present to us overcoming challenges of simulating EOR processes from the model size to incremental oil, and will tell us how they adapted the model to capture the impact of physical and chemical changes occurring in the reservoir. We invite to all the participants to write your questions and comments to Gisela in the chat, and they will be answered in the panel section. Many thanks, Gisela, for being with us today, and thanks for your presentation.
Hello, my name is Gisela Vanegas Cavas. I work for OMV Exploration and Production in Vienna, Austria. Today I'm going to present overcoming challenges of simulating EOR processes from the model size to incremental oil. This is a combined work with David Buch, Thorsten Clemens, also from OMV. I'm going to start the presentation with an overview of our alkali polymer study on the 16TH reservoir, which is an Austrian mature field. I'm going to follow with the research study on the optimum cell size for adequate incremental oil prediction, and I'm going to close with a reflection on the necessity for cloud computing and next generation simulators to overcome the modeling standards needed for EOR processes. 16TH is one of the largest reservoirs in continental Europe. We have conducted significant amount of work on this project, and it started with the characterization of the TAN number. We discovered that the 16TH has a TAN number of nearly 2, which is high, and this means that it can generate soap in situ when we inject an alkali. This soap represents that the interfacial tension is reduced, and we have confirmed with several lab experiments that the IFT reduction represents a great increase in the recovery. In the laboratory, we have conducted more than hundreds of phase experiments, up to 22 micromodel experiments, 18 plots, including different formulations, dead oil and live oil. And we acquired recently real core material, so we are currently performing new experiments on alkali interaction and more core fluorines. We have optimized our formulation, and our cocktail includes 2000 ppm of HPAM and 7000 ppm of sodium carbonate. We have previously done an interwell tracer test using conservative tracers, and we are currently injecting partitioning tracers also in an interwell study to quantify the remaining oil saturation. We have also done extensive simulation work, first on our core float experiments to characterize the alkali polymer, also on the potential pilot sectors where we performed stochastic modeling, and we obtained calibrated ensembles that have been used for the first predictions of our AP conceptual designs. You can find more on our work in different SPE papers. So this study was conducted on a cross-section. This was modeled between to 68 wells, and we used different cell sizes. We started with 30 centimeters by 6 centimeters, which we consider was our log resolution, and this resolution was fixed as our historical data. And we created models with 1 meter, 2 meters, 3 meters, 5 meters, and 10 meter cells that were also populated using our well logs for the sand distribution, the porosity, and the permeability. Using different seeds, changing the percentage of the core sands, and changing the setting spirograms, we generated 100 geological realizations for each grid. As I mentioned before, the model was set up between two wells, one considered the injector and the other one considered the producer. On the very fine grid, we ran the simulator, and the production recorded was labeled as our history data. Then we upscaled to our 5 grid sizes, 1, 2, 3, 5, and 10 meters, and we also increased the layer thickness to 12 centimeters. For each of these models, we upscaled our 100 realizations from the fine model using harmonic average for the porosity, a flow-based method for the permeability, and we calculated the phases for each of these upscaled models using the AMEFUEL flow zone indicator method based on the porosity and the permeability. For the simulation, we use a constant production rate of 1.4 cubic meters per day. The injector was set to replace the produced volume, so we are working under voidage conditions. We started injecting a tracer with water after 2 years a second tracer. So we have 2 tracer pulses, and in total 5 years of water flooding, chemical flood of 1 year, and follow-up waters for another 5 years. Once we got our 500 simulation results, the first question was, how can we analyze it? If we just look at the numbers and just calculate the average cumulative oil after the water flow and after the AP or the cumulative incremental, there is not much dissimilarity between them. But when we look at the time series, there are many things we can already notice. We can notice that we bracket better the production history from our superfine model with all our realizations, but we underpredict the cumulative oil at the end of the AP process. We also noticed that the shape of the curve doesn't correspond between the history and the simulated upscaled grids. So we decided to use principal component analysis to better understand and better compare the difference between our time series from the simulated models and the historical model or the fine model. The principal component analysis is an orthogonal transformation of the data that guarantees that the variance of the data is maximized. The first principal component is shown in the x-axis, and the second principal component in our case is shown in the y-axis. And each dot in our example, this is taken from Wikipedia, but you need to imagine that each dot will represent one time series, which is one simulation run out of our 500 runs. PCA can be used for dimensionality reduction, projecting each data point in these 2 principal components. You can choose, you don't necessarily need to use the second component, you could use the third or the fourth one, depending which one is giving you more information about the original data. This lower dimensional data preserves as much as the data's variation as possible. So this is a very great tool to compare time series. We started by comparing then the PCAs of our cumulative oil after the water flooding process and after alkali polymer. And we could observe first that in the water flooding, even though we saw bracketing when we were observing the time series, in reality the curves are very different to the historical data. We can see that around the historical data point, which is represented in pink, we have a few models from all different sizes, including the 10 meters grids. When we analyze the alkali polymer period on the right side, we can see that the history is surrounded or is close to by 10 meter grids realizations. However, it's not really fully bracketed. But using the cumulative oil will give us a wrong interpretation of the performance of our EOR process. Why? Because it's combining in the effect of the previous period of water flooding. What we really need to do is to determine the incremental oil. And this is the oil that we produce in each of these realizations if we compare the no further action, so continuing with water flooding or doing the AP. If we have these two scenarios and we calculate the difference, this is our incremental oil. This is the oil we are mobilizing by injecting the alkali that is reacting with the oil in the reservoir. We believe this is the right way to evaluate the impact of the chemical slug. In the time series, we can now see that the history is actually well bracketed, but not by the 10 meter grid, which is represented in blue, which is completely off. If we look at the PCA, it shows us exactly the same picture now. It shows us that the 10 meter grids responses are here in this part of the curve, while the history is lying in the cloud of the small sizes realizations. The conclusions of our studies are first, the PCA is an effective way of comparing time series and it improves the way we see data. The cell size has a large impact on the tracer and oil production, but this is case dependent. The maximum acceptable cell size should be based on the available data. So it's not the same if we only have production history as having also tracer data, which is shown to be informative about the displacements and the behavior of the saturations in the reservoir. We need to adapt to what we can see. And finally, the most important one is that the most reliable way to forecast the performance of incremental oil is by looking at the incremental oil production, and this requires cell sizes of at least 5 meters in order to better predict what is happening in the reservoir. This is much smaller than the current ones used in the industry or in-house, which are in general between 10 and 20 meters. So how to overcome these simulation challenges? If we think that currently we are working on models that are 10 to 20 meter cell sizes, this means that we have in the order of 5 million active cells. If we go down to 5 meters only, which is the uppermost, we are talking about 20 million cells models. This is much more time consuming. And on top of this, we have to also adopt these new EOR technologies coming, like nanoparticles, geothermal, geomechanics, carbon capture. It means that the complexity of the problem that we need to solve with the simulator is much, much higher. In the company, We are currently relying on cloud computing and next generation simulators to solve this problem. Last year, we performed over 25,000 simulation runs for our EOR projects, and we believe investing in this is the only way to overcome these changing challenges in the future. So I would like to close with this reflection. The most common objective for EOR studies is to generate incremental oil, and we simulate in order to predict this. All type of EOR processes increase the complexity of the conventional reservoir simulation because we are changing not only the physics by replacing oil with water, we are also changing chemistry in the reservoir, and we need to cope with this. We need to adapt our models in order to capture the impact of social transformations. The way we see to solve this problem is a combination of state-of-the-art hardware and software. And to keep the pace, we need to continue investing in R&D and in infrastructure so we can guarantee that the innovations that we achieve in the lab can reach our simulation models and eventually our real reservoirs out in the field. And with that, I want to say thank you for your time, and we'll be glad to answer any questions.
Thank you. Sorry, I was unmuted. Thank you very much, Giselle, for great presentations. Please welcome to put your questions into the chat, and as well, please fulfill the form. On the final part of our sections today, we are going to bring the panel alive. Thank you again for all of you to be here connected. We have around 50 people connected from this time, different schedule times. We have connected all the continents. Thank you. So with that, I would like to say to continue in our International Energy Agency Technology Collaboration Program, Enhanced Oil Recovery Insitu Reactions workshop today. Thank you. Let's continue with the next conference.
Of China University of This presentation will be developed by Dr. Lin Riji, Professor of China University of Petroleum, East China. He is the head of the Department of Energy and Power Engineering and the director of the Qingdao Engineering Research for Efficient and Clean Utilization of Fossil Energy. His main research interests are heavy oil thermal recovery, fluid flow and heat transfer, process energy saving, and thermal system optimization. He is reviewer for several journals as Fuel, Energy and Fuel, SPE Journal, Environment Pollution, Journal of Engineering Thermophysics, and Chinese Journal of Petroleum. Won 5 first, second, and third prizes for scientific and technological progress of China, Petroleum and Chemical Industry Federation, and 1 third prize for scientific and technological progress of Shandong Province. Published more than 100 journal papers, obtained more than 10 invention patents, and published 2 monographs. Dr. Rigi will present to us a study on supported transition metal catalysts for the sulfurization and viscosity reduction of heavy oil, and will tell us about 5 catalysts with different loadings that are synthesized for heavy oil catalytic desulfurization and viscosity reduction. We invite all the participants to send all your comments or questions in the chat, and they will be discussed in the panel section. So many thanks, Dr. Rigi, for being here with us and for your presentation.
Hello, everyone. I'm very glad to attend this conference and give a presentation today. My name is Lu Chang, a postdoctor from Dr. Lin Yuyi's group from College of New Energy, China University of Petroleum, East China. The topic I will give today is study on supported transition metal catalyst for desulfurization and viscosity reduction of heavy oil. Firstly, I'll give a brief introduction. Secondly is the technical rules. Then follows with catalyst preparation and characterization, and the catalytic viscosity reduction and desulfurization experiments. And in the end is the conclusions and the prospection. As we all know, heavy oil production plays a very important role in worldwide hydrocarbon development. The proven reserves of heavy oil in the world are about 815 billion tons, accounting for about 70% of the remaining reserves of global oil. And China is the fourth largest producer of heavy oil in the world, with reserves of about 4 billion tons, accounting for about 20% of the remaining oil reserves in China. However, heavy oil has very high viscosity, which leads to poor fluidity. Thus, it's very difficult to exploitation, gathering, and transportation. At present, the development method of heavy oil mainly include 4 types. The first one is conventional heating technology, like SAGD, FAS, and so on. And also, we can use physical method, microbial method, or chemical method to reduce the heavy oil viscosity. Among them, the Insitu catalytic upgrading of heavy oil technology, which based on the hydrothermal cracking reaction of heavy oil, has vast potential for further development because it can irreversibly reduce the viscosity of heavy oil. At present, China has a large amount of heavy oil production. The thermal recovery of heavy oil accounting for about 10% of total crude oil production. However, its energy consumption is relatively high. Taking Xinjiang oil field as an example, heavy oil production accounts for 1/3 of the entire oil production, while the energy consumption accounts for 2/3. Thus, in situ catalytic upgrading method is a promising method to recover the heavy oil, which can lower the reaction temperature and reduce the energy consumption by reducing the cracking reaction activation energy. However, this method still have some deficiencies. The first one is that the performance of the catalyst is not up to the expectation. And the second one is that the reaction temperature is still relatively high, and the application temperature range is relatively narrow. Thus, we would like to develop a kind of catalyst which have good catalytic performance on heavy oil viscosity reduction at a relatively low reaction temperature range. And to achieve this goal, we would like to use the solid acid catalyst as a target catalyst, because these kind of catalysts have relatively good performance and its modification is relatively flexible and easy. Two transition metal components A and B are selected as active ingredients, and the molecule C is used as a carrier, which can improve the overall structure stability of the catalyst. After preparation and characterization of the catalyst, we will test its desulfurization and viscosity reduction performance from 4 aspects as listed here. And here comes with the catalyst preparation and the characterization part. Firstly, the nano-supported catalyst with different loadings were designed and prepared. Then we characterize it. We use XPS to detect the valence state of the transition metals and verify the loadings of the active components. And the XRD method tests the composition of the catalyst by detecting the diffraction peaks of the carrier and active components. And the N2 sorption isotherm indicates that the catalyst has a mesoporous structure. The BT data of the carrier and the catalyst are shown in this table. The largest specific surface area can promote the contact between the active components and the reactants. And the large pore size can permit the free entry and exit of heavy oil macromolecules. And these 3 TEM scanning pictures shows the critical phases of the active components. We also did ammonia TPD test. The graph shows that the surface of the carrier, which is line A, has many weak acid sites, and after the active components are loaded, the exit area and the number of strong acid site increases in the high temperature zone, which is shown here. And the second graph is a TGA graph, which shows a good thermostability of our catalyst. And after all the characterizations and making sure the prepared catalysts are in line with our expectation, we would like to test the performance of catalyst on heavy oil viscosity reduction and the desulfurization. The experimental devices are shown in these pictures, mainly including high temperature and high pressure reactor and the rotary viscometer. And the experiment follows the typical procedure, and the experimental condition is shown here. Due to the time issue, I will not give a detailed description of it today. However, we have 7 groups of oil samples with different additives are used in the experiment to investigate different influence factors on catalytic viscous reduction and desulfurization. Group A works as a reference experiment. Only oil and water are added, and on this basis, hydrogen donor, the titulene, is added to group B, and the hydrogen donor and the molecule C is added to group C. And in group D, E, F, and G, except the hydrogen donor and the molecule C, catalysts with different loadings are added to the oil sample for the catalyzer reaction. And the catalyst usually in group D and E contains dual active components with different amounts. And the catalyst in group F, and G only contain one kind of active component. And we use the heavy oil from Bina oil production plant as the oil example. And the physical properties of the oil example are tested firstly, including the viscosity, SARA, and the element analysis of the oil example. We can conclude that the oil example is a non-Newtonian fluid with high content of heavy resin and asphaltene, and the degree of unsaturation of the carbon is very high. Then we test the catalyst destabilization and the viscosity reduction performance from 4 aspects. The first one is the influence of the hydrogen donor. Petroleum is added as a hydrogen donor here. The first graph shows the viscosity of the oil example at 50 degrees centigrade after reaction at different temperature. Group A has no hydrogen donor added, while the Group B has hydrogen donor added. It shows that the addition of a hydrogen donor inhibits the rebounds of the viscosity of the oil example after the reaction. That's because the combination of hydrogen atoms in the hydrogen donor with the reactive free radical inhibits the polymerization reaction of the hydrocarbons. And the second graph shows the influence of hydrogen donor or heavy oil destabilization. And the sulfur content in the oil example after the reaction of Group B decreases significantly. And the SARA table shows that the aromatic contents increase, which proves that the addition of hydrogen donors promotes the hydrothermal cracking reaction and helps the upgrading of heavy oil. And we also did the FTIR test, and the spectrum of heavy oil Group A and Group B oil examples are shown in the left-hand side graph. And there are 4 main absorption peaks in the oil example, which represents the absorption vibration peak and the stretching vibration peak of the methyl group and the methylene group, respectively. The peak intensities are shown in the following table. And it can be found that the absorption peak intensity of methyl and methylene groups increases, which means their content increases after addition of hydrogen donor. And the picture on the right-hand side is the element analysis of oil examples. And it can be found that the hydrogen-carbon ratio increases after the hydrogen donor is added. Next, we will investigate the effect of different types of catalysts with different loadings on the viscosity reduction. And the oil example is prepared on the basis of the presence of hydrogen donor, which is Group B. All the viscosity reduction experiments were conducted at the temperature of 280 degrees centigrade. The first figure shows the viscosity reduction rate of the oil example catalyzed by different catalysts. And Group D and E have the best viscosity reduction performance. And the second figure shows the desulfurization rate of different catalysts. Group D, E, and F has relatively good desulfurization performance. And this figure shows the quantity change of SARA of the oil example. We can see the Group D, E, and G has relatively good coke production inhibition performance. cause the contents of S14, which is a yellow bar, is greatly reduced. And from the element analysis, we can see that the group D and E has the highest hydrocarbon and hydrogen and carbon ratio, which indicates a good heavy oil upgrading performance. Then the role of carrier C, active components A and B, in the viscous reduction process was analyzed. The FTIR result of our example shows that the carrier C in group C can promote the methyl production due to its strong surface acidity and better pore structure. And active component A can promote the production of methyl and methylene. And component B also has some certain effects on viscosity reduction, but not the main factor. However, in the previous slide, we can say that the main function of component B is to reduce the S14 contents because it can inhibit the production of coke. And the previous result shows that group D and E have the best performance. And consider the economic issue, group D was selected to study the effect of reaction temperature. And group B is conducted as the reference experiment. The first figure shows the viscosity reduction rate of the oil examples of group B and group D. After the reaction at different temperatures, the viscosity reduction rate increases from about 10% to nearly 30% at 160 degrees, and reaches more than 80% at 320 degrees. And the second figure shows the sulfur content of the oil example after reaction at different temperature. It can be found that the desulfurization effect increases with the increase of temperature. And these two figures shows the contents of SARA of group B and group D. And it can be found that the heavy oil components of oil example decreases significantly with the increase of temperature and the action of catalyst. And the last figure shows the hydrogen-carbon ratio in the oil example after the reaction. And it shows the catalyst in group D can enhance the upgrading effect, and the effect is proportional to the temperature. Finally, we investigate the influence of the amount of catalyst on the viscosity reduction. Group D was taken as the research object, and the experiments were conducted at 280 degrees centigrade. The result shows that with the increase of the catalyst addition, the viscosity reduction rate gradually increased, and the sulfur contents in the oil example decreased. And the heavy components decreased, and the light component increased in the oil example. And the viscosity reduction effect tended to be stable when the addition amount is about 1 weight percentage. And through about research, we can draw the following conclusions. The first one is a supported nanocatalyst with metal oxides A and B as active components and the molecular sieve C as a carrier was designed. The second is the hydrogen donor can effectively reduce the viscosity rebounds of heavy oil after the reaction. And we also found the dual active components have a stronger viscosity reducing effect than single active components. And the catalyst is effectively at low temperature and stable at high temperature, and the viscosity reduction rate reaches nearly 30% at a low temperature of 160 degrees. And the viscosity reduction rate reaches over 80% at a high temperature of 320 degrees. And in the future, we also would like to further promote the low temperature activity of the catalyst while ensuring the stability of the catalyst under high temperature condition. And for the in situ upgrading technology of heavy oil, we can also take the complex core environment of the formation as a consideration and investigate the migration and the transfer law of the catalyst. That's all my presentation today. Thanks for your attention.
Thank you very much. Really appreciate it. It was a great presentation. Thank you, Dr. Chan Liu and Professor Rigi Lin for this intervention. And thank you all of you that have been connected today. What we would like to bring is these in situ reactions, how can come together on our different EOR projects. So please, I welcome you to state your questions on the chat. We will bring all the questions into the panel section. And as well, please fulfill the form. We have it there. And with that, I would like to say thank you to all of you. We have been unmute everyone just to the comfort of everyone has. Myself as well was unmuted. Sorry, the host will become live later on. So with that, I would like to say thank you to all of you again, and we go for our next presentation.
Our next presentation will be developed by Dr. Himanshu Sharma, Assistant Professor of Chemical Engineering at the Indian Institute of Technology, IIT Kanpur. His research interests include understanding the transfer of simple and complex fluids for energy and environment-related applications. He has an extensive experience of gas and chemical-based enhanced oil recovery techniques, including the surfactant fluoring, gas and foam fluoring, and wearability alteration. He holds a PhD in petroleum engineering from the University of Texas at Austin. He has a master and bachelor from the Indian Institute of Technology, both in chemical engineering. He has worked in the R&D departments of Total in France and Petronas in Malaysia at different times in his career. Dr. Sharma will present to us geochemical interactions in alkali surfactant polymer fluoring. We invite all the participants to write your questions or comments for Dr. Sharma in the chat. They will be answered in the panel section. Many thanks, Dr. Sharma, for being with us today and for your presentation.
Hello everyone, my name is Himanshu Sharma. I'm an assistant professor in the Department of Chemical Engineering at the Indian Institute of Technology, Kanpur. And in this presentation, I will be talking about geochemical interactions in alkali surfactant polymer flooding. And before I begin, I would like to mention that whatever results that I'll be showing in this presentation, that work was conducted at the University of Texas at Austin, where I was a PhD student as well as a postdoctoral fellow. So when you think about geochemical reactions in the subsurface, you can think of this as a reaction between different species. So you can have species in the oleic phase, for example, organic acids and bases. Similarly, in the gaseous phase, you can have gases like CO2 and H2S. In the aqueous phase, you can, of course, you have some ions, but in the case of ASP flooding, you also have alkali surfactants and polymers. And last but not the least, the rock itself is made up of different minerals. For example, in carbonates, you have minerals such as calcite and dolomite. In sandstone, we have silica and clays. And in addition, you can have other minerals in small amounts, such as siderite and anhydrite. And when these phases come into contact, the species that are present in these different phases react. And in most cases, in some cases, these reactions can be unfavorable, and that can lead to changes in porosity and permeability. But even otherwise, these interactions can change the composition of the injected fluid. So the composition that is actually present in the ground can be different from the composition that you inject. Alternatively, the composition of the produced fluids can be different than the fluids that are actually present in the subsurface. And similarly, these interactions can also lead to changes in interfacial tension as well as wettability. So therefore, understanding the role of these geochemical interactions in EOR processes become important. So here I'm just giving you a brief background of ASP flooding. I'm sure most of you are aware of this. After water flooding, so after primary and secondary flooding, you leave about 50 to 70% of oil due to high interfacial tension between oil and water, as well as the reservoir heterogeneity and viscous fingering. And many lab studies and field trials have shown that ASP flooding is very effective in recovering this oil that is left behind after primary and secondary flooding. ASP flooding, so these are the components of ASP flooding that I'm sure all of you are aware of. We have surfactants that lowers the interfacial tension between oil with oil, and that helps in improving the microscopic sweep efficiency. We have a polymer that provides you the favorable mobility ratio and increases the macroscopic sweep efficiency. And then you have an alkali that lowers surfactant absorption and generates in-situ soap. So in my presentation, I'll be mostly talking about interactions of alkali in the subsurface. So what are some of the advantages and challenges of an alkali? The first advantage is that when you use an alkali, it can lower the absorption of anionic surfactants on rock surface. And that is because when you increase the pH, your rock becomes negatively charged. So that I'm showing you by this reaction. You can also see that here I'm showing you zeta potential as a function of pH of a particular rock. And you can see that the zeta potential becomes more negative as you increase the pH, and that leads to lower surfactant absorption that is shown here. So here I'm showing surfactant absorption without any alkali and with alkali. And you can see that the absorption is lower when you add an alkali. And that is because now your surfaces are more negatively charged at a higher pH. Second, the alkali also generates in-situ surfactant if your oil is acidic, and that is advantageous because when you generate soap in situ, then the amount of synthetic surfactants that is needed, that get reduced. And the third is that these are the main, but surfactants also help in stabilizing some of the the alkali also help in stabilizing some of the surfactants, such as sulfate surfactants. So at temperatures more than 60 degrees, increasing the alkali can stabilize the sulfate surfactants. So these are some of the advantages. What are the challenges? Of course, you need water softening when you're using an alkali, because otherwise your divalent cations can precipitate. Some of these alkalis, and under some conditions, they can undergo unfavorable geochemical interactions, and that can lead to scaling at the production well, permeability damage, excessive alkali consumption, and pH propagation delays. And for field operation, since a large amount of alkali is typically needed for a field operation, storage and handling is also a challenge. Now, what are some of the characteristics of a sort of an ideal alkali? One is that it should provide you a high pH, more than 10, so that you can lower the surfactant adsorption, and the alkali can generate soap in situ. In addition, your alkali should be able to propagate a high pH through the porous media without causing changes to the properties of the porous media, so without undergoing any reactions or changing the permeability. Now, in 1970s and 80s, most of the alkalis that were studied, they were fairly strong alkalis, such as sodium hydroxide, potassium hydroxide, sodium silicate. These alkalis provide a very high pH, more than 12, in some cases 13, and as a result of which these alkali undergo excessive reactions with the rock. Most of these studies were performed in sandstone rocks, although some were also performed in carbonates. And what these studies found that these alkalis are too strong for an ASP flooding. Due to these reactions, you can expect pH propagation delays, excessive alkali consumption, permeability damage, and so on. So therefore, people have now started moving towards a milder or mild alkalis, and sodium carbonate is an example of that. So with sodium carbonate, you get a pH of about 11 when you add 1% sodium carbonate. And sodium carbonate is found to be effective in lowering surfactant adsorption as well as surfactant adsorption in both sandstone and carbonates, as well as form in situ soap in case of acidic crude oils. The reaction of sodium carbonate is much less compared to the strong alkalis, and there is one exception that I'll discuss in the following slides. In addition, sodium carbonate precipitates divalent cations, so you need water softening, but then you can also expect divalent cation precipitation when you inject this alkali in a reservoir that is a formation brine with high amount of or with the divalent cations. And these precipitations can also lead to changes in permeability. So that is one thing to keep in mind. Similarly, sodium metaborate is another alkali that we have studied recently. And the kind of pH that you get is around 10.5 with 1% sodium metaborate. And sodium metaborate is somewhat tolerant to divalent ions, divalent cations. Now, this is not a very high concentration, but compared to sodium carbonate, it has more tolerance to divalent cations. That you can also see here. This was one of the experiments that we did, where we started with a 2000 ppm calcium in DI water, and we increased the amount of sodium metaborate. So here I'm just showing the boron concentration. And we found that as you increase the concentration of sodium metaborate, your calcium starts to precipitate. So these are equilibrium concentrations. So even after precipitation, you can see some amount of calcium remains soluble. So therefore, sodium metaborate has somewhat higher tolerance to divalent cations. We also found that sodium metaborate is effective in lowering adsorption on sandstone and carbonates, almost same as sodium carbonate. So that is what I'm showing here. This is the static adsorption test that we performed, and we found that, so these are 3 tests. One is without an alkali, and these 2 are with 5000 ppm sodium metaborate and sodium carbonate, and we found that we saw reduction in surfactant adsorption both with sodium metaborate and sodium carbonate, and the adsorption values that we found in presence of these 2 alkalis were very similar. And also sodium metaborate can generate in situ soap with acidic crude oils. Then ammonia is also an alkali that we studied recently. And one of the advantages of ammonia is that it gives you a high pH with a small amount of alkali needed. And that is because ammonia has a low molecular weight compared to sodium carbonate. So you need a less amount of ammonia. It is found to lower adsorption in sandstone and carbonates, similar to sodium carbonate that you can see here. With ammonia and sodium carbonate, you get lower adsorption, and it generates in situ soap with acidic crude oils. However, ammonia does not precipitate calcium ions, unlike sodium carbonate. And we'll see what are the implications of that. So here I'm showing you results from this study, these three plots, where they found that by adding ammonia, as the pH increases, the surfactant absorption goes down. However, because ammonia does not precipitate calcium ions, as the calcium concentration increases, you can see that the adsorption or the retention also increases. Right, so these calcium ions that are soluble in ammonia interact with the surfactant and increases the adsorption of surfactants. So there are two effects. pH, on the other hand, is trying to lower adsorption, but calcium ions increase adsorption. And that is because when you increase the calcium ions, your rock becomes more positively charged, and that results in increasing the surfactant adsorption. Now, most of the previous studies were performed in sandstone. However, some studies are now also recently performed in carbonates. And that is because carbonates are typically at higher temperature and higher salinity. That is challenging because, to find surfactants that can work under these conditions. They have low permeability, they are highly heterogeneous, and they have a complex mineralogy. Particularly, although calcite and dolomites are not that soluble, but anhydrite is fairly soluble, and that makes it difficult for ASP flooding to apply on carbonate reservoirs. And what are the challenges of anhydrite? So anhydrite is fairly soluble in water. So if you inject DI water in a reservoir that has anhydrite, then you can expect about 1000 to 2000 ppm of calcium coming from the rock due to anhydrite dissolution. So that is a high amount of calcium that you get from the rock. And in presence of alkali, you can expect that these calcium ions interact with the, for example, in case of sodium carbonate, reacts with carbonate ions and precipitates the calcium carbonate. And this reaction continues until either the alkali is finished or the anhydrite is finished. Similarly, if you have sodium hydroxide, then you form calcium hydroxide. So because of these precipitation, you have alkali consumption, your pH propagation is delayed, and so on and so forth. What is more worrying is that even a small amount of anhydrite, as low as 0.18%, which is difficult to detect from XRD analysis, is enough to cause severe damage to your ASP flooding. So we did some experiments where we studied the experiments and simulations to study the impact of injecting sodium carbonate in rocks that have gypsum. So these are carbonate rocks with gypsum. And as you would expect that when you add sodium carbonate, you would expect a precipitation of calcium carbonate in presence of sodium carbonate. And that is what I'm showing here. So these are the simulation plots where I'm plotting the effluent pH as a function of pore volume for two cases. In the first case, when you do not have any gypsum, then your pH comes out to be same as the injected pH, around 11. On the other hand, if you have gypsum, then the effluent pH goes down to about 9. And that is because of this precipitation reaction that is going on. So you have high alkali consumption, pH propagation delays. And in this experiment that we conducted, we found that the rock becomes completely plugged because of these precipitation reaction. Then we also looked at the effluent ions, and we found that because of this reaction, the sulfate concentration increases to a very high value. So here in the effluents, we were measuring sulfate as high as 23 or 24,000 ppm, although we did not inject any sulfate in the injection brine because the injection brine had only sodium carbonate and sodium chloride. So this sulfate is coming from the dissolution of anhydrite and the precipitation of calcium carbonate. And we did not see any calcium ions because although when sodium, this anhydrite is dissolving, you would expect some calcium, but that precipitates because of sodium carbonate, and therefore we did not see any calcium in the effluents. We repeated similar studies with sodium metaborate, same core or a similar core with gypsum or anhydride. And we found that sodium metaborate was able to propagate the pH, a high pH around 10.2 at about 1 pore volume 1.5 itself. Our pH was about 10.2, and the extent of reaction was much less severe compared to sodium carbonate. As you can see that the calcium concentration is around 300 ppm, and the sulfate is also around 2,000 to 3,000 ppm, not as high as 23,000 or 24,000 ppm that we saw in the case of sodium carbonate. Similarly, we also performed a test where we injected ammonia in presence of anhydride, and we found that since ammonia has tolerance for calcium ions, we saw very good pH propagation. So at 1.5 pore volume injection, our pH was already similar to the injected pH of about 11, and our sulfate and calcium ions were in equimolar amount. So that means we did not see any precipitation when we injected ammonia. So at least we found that ammonia and metaborate, sodium metaborate, are better in terms of propagating the pH, although this does not automatically translates into a lower surfactant absorption. So more studies are needed to confirm that. Now there's one more point that I wanted to mention, that is that although interaction of alkali is important, but these geochemical interactions are also important for surfactant phase behavior and polymer stability. So you can, for example, we saw that when you have anhydride in your reservoir, then you can expect about 500 to 2000 ppm calcium ions. And therefore, if you do not have any calcium ion in your surfactant slug, then calcium as high as 2000 ppm can come from the rock due to anhydride dissolution, and that can affect your surfactant phase behavior. So if your surfactants are not tolerant to hardness, then you would lose ultra low IFT. Also, because of these divalent cations, there may be a shift in the optimum salinity that I'm showing you here. So here I'm showing you solubilization ratio as a function of TDS. So this is the optimum salinity when you do not have any calcium, and the solubilization ratio is about 12 when you don't have any calcium. But then when you add calcium, 1000 ppm, you can see that the optimum salinity shifts to around 45,000 ppm, and your solubilization ratio also goes down slightly to about 11. But what is more worrying is that your change in optimum salinity is about 20,000 ppm. And therefore, if you design your ASP flood according to this phase behavior, then you can expect that your experiment or your study will not be effective because your actual phase behavior is different. So therefore, it's important to consider the effect of these interactions, particularly in case of anhydride, not just on alkali, but also on surfactant phase behavior, but also on polymer stability, because some polymers are not tolerant to hardness, particularly if the degree of hydrolysis is very high for a polymer, for an acrylamide polymer. So with that, in summary, we know that alkalis are useful because they can lower surfactant absorption and generate in situ soap. But strong alkalis or the alkalis that exhibit excessive reaction with the rock can be detrimental for ASP flooding because they can cause permeability damage, excessive alkali consumption, pH propagation delays, and so on. And therefore, it is important to consider rock mineralogy when designing an ASP flood. And recent studies have found that sodium carbonate, sodium metaborate, and ammonia are better compared to the strong alkalis that were used in the 70s and 80s. And last but not the least, the effect of geochemical interaction on surfactant phase behavior and polymer stability is equally important. And these are some of the references that the results that I showed in this presentation. And I would like to acknowledge Dr. Kishore Mohanty, Dr. Gary Pope, and Dr. Upali Veera Surya, who were my PhD supervisors, as well as I worked with them during my postdoctoral fellow at in the Department of Petroleum Engineering at the University of Texas at Austin. And thank you very much. and I'll be happy to answer any questions you may have. Thank you.
Our next presentation will be developed by Dr. Yongxi Tang, Associate Professor of Research Institute of Petroleum Exploration and Development. He is the chief of Air Injection Laboratory. His main research interests are heavy oil in situ combustion and light oil air injection. Won 2 first prizes for scientific and technological progress of China Petroleum and Chemical Industry Federation, and won 2 prizes for scientific and technological progress of CPNC. Published more than 20 journal papers and obtained more than 10 invention patents. Dr. Tang will present to us research on oil oxidation process during oil-filled air injection production process, and will tell us about the study the high temperature oxidation kinetics of oils with different viscosities using thermogravimetric analysis. We invite all the participants to write your questions or comments for Dr. Tang in the chat. They will be answered in the panel section. Many thanks, Dr. Tang, for being here with us today and for your presentation.
Greetings, ladies and gentlemen. It is my honor to share our research on oil oxidation during oil-filled air injection production process. This is the outline of my presentation. First, I will introduce the background of our research. China ranks 5th in the world in heavy oil and oil sand recoverable resources, which are mainly distributed in the Bohai Bay Basin and the Zhongguo Basin. Liaohe and Xinjiang oil fields have the largest heavy oil reserve. For many brown oil fields with heavy oil in China, the oil production rate and oil steam ratio are both quite low. Evaluation for suitable EOR methods for these oil fields is quite important, and in-situ combustion is considered as a good candidate. In-situ combustion is also called fire flooding. For this production method, an electric heater or an igniter will be inserted into the reservoir and heat the reservoir to 500 degrees Celsius. And then we injected air. Normally, 10% of the heavy oil will be burned as fuel, and 90% of oil will be produced for one-dimensional combustion tube test. For field operation, nearly more than 60% of oil will be produced for by in-situ combustion method. So, PetroChina began the in-situ combustion pilot in the year 2009 in Hongqian Block, Xinjiang oil field. Before in-situ combustion, this block is developed by steam injection, which is a system silic steam stimulation and steam flooding. For the steam injection method, the recovery factor is 29.5%. Then the reservoir is depleted and shut down for 10 years. In the year 2009, the in-situ combustion pilot began. And after 10 years, by the end of 2019, the accumulated oil production of in-situ combustion is 155,000 tons, and the state recovery degree of in-situ combustion is 36%. The average monthly production of in-situ combustion is 1,200 tons, and the accumulated air-oil ratio is 2,900 cubic meters per cubic meters. So the pilot test is very successful. The vertical wire fire flooding pilot in Hongqian block shows very promising results. So the in-situ combustion is used as strategic EOR method for brown oil fields with heavy oil in China. For in-situ combustion process, the oxidation of crude oil in the reservoir is quite complex. Normally, for heavy oil and different oil, we think that for heavy oil, most reduction heat is released by the HTO high temperature oxidation process, and the low temperature oxidation process releases very little heat. But for the light oil, the reaction heat is mainly released by the low temperature oxidation process, and the high temperature oxidation process releases very little heat. For heavy oil in situ combustion, in the reservoir, it can be divided into many regions. For example, combustion zone, combustion front, and cooking zone, steam zone, oil bank, and the residue oil area. In these regions, the most important one is the combustion front. The reaction here is high temperature oxidation. It releases most of the heat for this process and provides energy for the in-situ combustion. But for the study of in-situ combustion with different oils, different researchers published data with different apparatus. The results are quite different. Because the activation energy of high temperature oxidation influences the reaction temperature, so the combustion front temperature may vary with each other, may have a big difference. So the application of in-situ combustion on heavy oil reservoir could be limited by the oxidation kinetics of oils. Another problem is for high pressure in-situ combustion test, we found that the tubing and casing were damaged by the high reaction heat during electric ignition process. This pilot test is carried out in the Tuha oil field, and the reservoir pressure is 22 megapascal. Influence of pressure on reaction rate and reaction heat need to be studied. Now I will introduce our research about HTO kinetics of different oils. We use TGA to study this process. TGA can record the sample weight during the heating process of the oil sample or the coke sample. First, we studied the influence of sample preparation methods. For the oxidation with pure oil sample, there are multiple reaction peaks in HTO regions. That is because for this oxidation process, the oxidation only takes place on the surface of the oil. The bottom oil can't reach the oxygen, so the reaction is not even. So we mix oil with silicon oxide, so oxygen can pass through the porous space between silicon oxide particles. All coke will be deposited on the silicon oxide surface, so they can react evenly during the experiment. So this result can be used to calculate the intrinsic oxidation kinetic parameters. We also studied the calculation method influence. These two figures show the results of two single curve kinetics determination methods. We can see for the same oil, if we use two different single curve kinetic calculation methods, the activation energy result is quite different. The reason is that for this method, we use only single reaction curve to calculate three different parameters: activation energy, pre-expositional factor, and reaction order. This can cause a very big errors. So we use isoconventional calculation method to avoid the influence of fuel mechanism functions which means we didn't calculate the reaction order or other forms of mechanism function of the fuel. In these conditions, we use different heating rates test result and get the experiment data with the same conversion rate. So at this condition, we can calculate the activation energy and the pre-expositional factor A very exactly. We choose some oils from PetroChina air injection field pilot. In these oils, there are some light oils with the viscosity about 20 to 45 at 50 degrees Celsius. And we have some heavy oils. The viscosity is about 2,000 to 40,000 centipoise at 50 degrees Celsius. For these different oils, the oil property and the viscosity are quite different, but we can see at the same reaction conditions, different oil have similar reaction temperature region. For LTO reaction, the temperature region is about 200 degrees Celsius to 400 degrees Celsius. And for high temperature reaction, different oil show the same temperature region is larger than 400 degrees Celsius. In order to calculate and compare the activation energies of different oil from both light oil and to heavy oil, we use two other different isoconversional methods to calculate. We can see with these three isoconversional methods, different oil, although the viscosity are quite different, but they have the similar, very similar high temperature oxidation activation energy. The activation energy is about 130 to 150 kilojoule per mole. We also calculate the high temperature oxidation kinetics parameters for other carbonaceous material fuel. For example, the soot captured from diesel engine and the commercial pure carbon with carbon content 99.5%. So for these carbonaceous fuel, the high temperature oxidation activation energy is also in the same range, 150 kilojoule to about 170 kilojoule per mole. So we can see for high temperature oxidation with different property oils and other carbonaceous fuel, the activation energy are in the very small range from 130 to 170 kilojoule per mole. So for different oil with different viscosities, we can have the same high temperature reaction temperature region. In order to explain this, we carry out the kinetic cell experiment. For kinetic cell experiment, we fill the reactor with oil sand in the middle, and then heated the kinetic cell temperature linearly to 600 degrees Celsius. And we measure the outlet oxygen, carbon dioxide, and carbon monoxide. So for these two figures, with different two oils, kinetic cell oxidation results, we can see for the red line, it represents the oxygen difference of inlet and outlet. And the blue line represents the oxygen in the produced carbon dioxide and produced carbon monoxide. So when reaction temperature is larger than 400 degrees Celsius into the high temperature oxidation region, we can see the depleted oxygen are the same of the oxygen in the carbon dioxide and carbon monoxide, which means for these oxidations, the fuel is mainly the carbonaceous coke, and the content of hydrogen is very small. The third part is our research about crude oil oxidation heat effects. In this part, we use three apparatus, Mittler, TGA, and DISC apparatus, TGT, accelerating rate calorimeter, and the TA company Q20P, pressured DISC apparatus. First, we studied the DISC curve at an atmospheric pressure to study the oxidation heat effect of different oil with different viscosity. So for these 6 samples, 2 are light oil samples and 4 are heavy oil samples. We can see different from previous research, heavy oil also have very prominent LTO reaction heat effect. And for light oil, the HTO reaction heat content is also very large, but it is nearly half of that of heavy oil. The reaction temperature region. For LTO reaction temperature region, light oil and heavy oil have nearly the same temperature region, and for HTO, also nearly the same temperature region. If we compare the heat of LTO and the heat of HTO, it is at nearly the same amount. But for the LTO, oil sample will react and release heat. But for HTO, only 20% of oil will be converted into coke. And this coke will release the reaction heat of HTO. So if we consider the specific heat of fuel, HTO is much higher than LTO. So for field operation, if possible, we should operate the in-situ combustion at HTO mode because it is much more thermal efficient. For the DST test, we can see that heavy oil can produce the reaction heat at low temperature oxidation region, about between the 200 degrees Celsius to 400 degrees Celsius. But below the 200 degrees Celsius, DSC cannot measure the reaction heat. So we use the accelerating rate calorimeter to study this process. We measured the arc test results with 5 different oils. The red one, blue one, and the purple one. The first 3 ones are the light oil result, and the last 2 ones are the heavy oil results. So we can see in the temperature region from 160 to 240, the heavy oil also have a very prominent reaction heat effect, which is not smaller compared with that of light oil. So for heavy oil, it can have a very different heat release region compared with HTO. Then we studied the influence of pressure and oxygen pressure on the oxidation heat effects. When we increase for the Liaohe and Tuha heavy oil, when we increase the pressure of reaction, we can see the temperature of both LTO and HTO both decrease. But for HTO, the heat itself didn't, the pressure didn't increase the HTO reaction heat amount. But for LTO, increasing pressure will increase the LTO reaction heat. That's because for HTO, the fuel is oil. So when pressure is increased, more oil will be contained in the thermal holder and react with oxygen and release the heat. These results are the 2 different light oil, the influence of pressure. We can see when we increasing the pressure, the LTO heat also increase a lot. And when reaction pressure is high, we can see a very sharp reaction heat peaks. For the influence of oxygen fraction, we carry out these two tests at the same pressure, but with different oxygen fraction. We can see when we increase the oxygen fraction, the reaction temperature also decrease for both heavy oil and light oil. But for the reaction heat, oxygen fraction didn't influence the HTO reaction heat, but increase the LTO reaction heat. For these two tests, we compare the results with the same partial pressure, two different tests. For these two tests, the pressure is different and oxygen fraction is different, but the partial pressure oxygen is the same. And we can see these tests are nearly the same. So which means for the reaction of both LTO and HTO, the reaction rate is proportional to the oxygen partial pressure. These test results also confirm this conclusion. So in final conclusion, TGA apparatus and ISO conversion methods were used to study the HTO kinetics of different oils. The activation energy range for 3 oils were 130 to 154 kilojoule per mole. Kinetic cell and effluent gas analysis technique were used. Fuel composition were calculated by the effluent carbon dioxide, monoxide, and oxygen concentration. The results show that the fuel of HTO reaction were coke with very low hydrogen content. Although the viscosity and compositions of oil were different, the fuels were similar. So TGA analysis showed similar HTO kinetics for different oils. Oxidation test showed that oil samples with different viscosities have similar LTO reaction temperature region and HTO reaction temperature region. Heavy oil samples also have high LTO heat effect. The measured reaction heat of HTO by unit mass of coke is larger than that of LTO. Oxygen partial pressure has strong influence on light oil LTO reaction heat. When pressure or oxygen fraction increase, LTO heat of light oil sample increase. Thank you. That's all for my presentation. I'm glad to answer your questions.
Thank you very much. Really appreciate it, Dr. Yu, for your presentation. It was really a pleasure to have all of you. Please remember, at the next presentation, we're going to have our panel discussion with questions, and we will looking forward to have all of you here. And thank you for the speakers that are already connected from different time zones right now. So please add your questions into the chat. Finalizing our next presentation, we will come together to do our panel discussions. So with that, I would like to say thank you all of you, and please welcome our next speaker. Thank you.
Our next presentation will be developed by Dr. Walid Albazaz. He is an associate research scientist for the Kuwait Institute for Scientific Research. Dr. Albazaz's research specialty is in carbonate reservoir characterization through integration, with the main focus in extreme heavy oil heterogeneity and unconventional imaging solutions. Other of his research topics are novel hybrid water recipe for EOR, weightability contact angle measurement in EOR, and heavy oil reservoir. Dr. Albazaz will present to us unconventional EOR white. He will invite us to think outside the pipeline and how to use EOR techniques at a non-conventional dimension. Please stay with us. Remember to send all your comments or questions in the chat, and they will be discussed in the panel section. Thank you so much, Dr. Albazaz, for being here with us and for your presentation.
Good morning, everybody. My name is Dr. Walid Al-Bazzaz, and I'm from Kuwait Institute for Scientific Research at the Petroleum Research Center. Today, I'm going to talk to you about the unconventional EOR and my experiment in the technical avenues, and hopefully we can share some ideas with you and tell you about our roadmaps and what kind of innovation and technology needed in the EOR. In the beginning, we're going to start with objectives and then going to portray some strategic platforms. Then we'll talk about the market and where it is heading and how the fundamentals are changing it. And the new technology, I have a new technology that can help EOR. One of them is the dry heat technology, what we call it HADAD, or the hot dry air diffusion. The second is the low salinity water flooding. And third is the understanding the waterability phenomena in the EOR studies. And some future solution innovation and avenues that we can suggest for you. So our motto is the more oil, the better we like it. So the objective for any EOR R&D program is to advance the stimulation, advance reservoir characterization, and advance the drilling technology, because these are driving the efficiency and the production improvement in our business at the EOR. So basically, we want to have increased the knowledge and awareness of the new game-changing information that is giving increasing difficulty in our unconventional technology and our changing economics that makes the production difficult economically and environmentally and all these kind of avenues. So the strategic platforms, we have the conventional EORs that is mainly maintaining the lower the crude oil viscosity and also increase the crude oil permeability. So together they are improving the mobility of the crude oil and also improve the reservoir waterability. And we like to see it more water wet, so that can help displacing the oil outside the reservoir into the pipeline and the production wells. And also we're gonna have EOR processes, the conventional, which is chemical EORs, thermal EORs, and gas injection EORs. Monitoring and information system of our technology, that's always going to be there. Logistics and distribution, and consumer markets, the supply and demand. This is basically our challenges in the conventional EOR. Now, we're gonna suggest some unconventional EOR technology because there is a lot of improvement in the nanomaterials. So we need to come up with a new purpose engineered chemicals with nano and with other materials, with polymers and so forth. Also, if you inject it, then you trace it. So we're gonna have to invest a lot in our tracer, because everything we inject in the reservoir, we have to trace it and see if it is working, not working, hitting the targets and so forth. So tracer programs, we're gonna see a lot in the current and future EOR programs. And also we're gonna have to work on the energy efficiency, part of the economical equations. Also to have a integrated digital transformation. This will help us maintain a lot of our efficiencies and regarding the reservoir characterization and others. We want to have the information faster. We want to have it robust. We want to have it cheap and all these kind of things. So we need to invest a lot in the digital transformation. Also, we need for the future EOR and unconventional, we want an unconventional human factor and the project teams. The human factor, in the old days, we needed petroleum engineering. Right now, we need a hybrid of petroleum engineer and maybe some other engineering and economics and computer engineering, IT, electrical engineering, mechanical engineering. So the petroleum engineer by itself is not going to be equipped enough for the future EOR. So we need to invest a lot in the human factor. Also robotics to minimize the error that the humans can make, and also to help our automation and faster production. Artificial intelligence solutions is going to be very important in the future of the EOR operations. Production of EOR crude oil transfer markets. Sometimes we invest a lot of money in heating up the reservoir and enhance the reservoir. But as it gets to the surface and to the journey that's going to go to the client, it cools off and it's solidified, and that could cause a lot of problems. So what we needed actually is to have a transfer markets in order for the EOR to survive in the future. So EOR market fundamentals are changing. We see that the changes are all opportunities, as a matter of fact. We look forward to see the economics and the demand and the unconventional other trends that's coming. We see in the avenues of the economy, can big oil companies sustain and save, improve their efficiency, capital efficiency? I think all oil companies right now, from the pandemic and from the weak demand, start to have eroding their capital. So 5 years ago, there was a big campaign cutting the cost of the CapEx to 45%. Right now, it's a very irrational target. So we are looking to find other avenues that's cheaper, and in order for the companies can maintain low cost of production. And that's the main targets that it seems that the big oils are slipping away. Cutting costs, CapEx is irrational because there is a lot of heavy technologies, and they all require maintenance and require equipment and new technology and invention and purposely built. So cutting costs in the CapEx, maybe in the operations, yes, in the OpEx, but in the CapEx, it might be an irrational target. We also face more market fundamentals that are changing in the weak demand. We saw that in the pandemic. But the truth of the matter is that whenever we're going to have a weak demand, is going to create an oil storage. So oil storage is the new concept, creating a glut in the supply and hence price volatility. That's going to be a very major challenge for the EOR crude oils. Also, adding more salt to injury, there are a lot of unconventional new trends coming to the table. And I have here mentioned 10. As you see in the red colors, they are all gas. So the future is going to be in the gas, the natural gas. So the natural gas is the actual threat to the EOR crude oils. So that can be an opportunity if we know how to balance between the natural gas and the EOR crude oils. We don't want to see the EOR crude oils facing the same future as the coal industry in the world. But if it keeps going in the same path, it surely is going to catch up. Okay, this is my first technology that I was playing with in the lab. I called it Haddad, or the hot dry air diffusion. It's basically dry heat technology. I get the reservoir and just have heat and extracts the crude oil from the other end. In the lab, you can do so many wonderful games and toys and experiments. But the truth of the matter is to want to push them through in the real lives, in the upscale, the pilot plants, and in a pilot scale or in the full-fledged scale. Right now, this is just to prove the benefits of this technology. So what is it this technology is all about? As you know that I'm from Kuwait, and Kuwait is a desert country. Water is always precious, and it has always in short supplies. So we want to think about a technology that utilizes no water, basically. So as we know that the steam requires water, and fresh water is the better. Cyclic steam, same deal. Steam assisted gravity drain SAGD, also the same thing. So our motive was to propose a technique that require or exclude the use or the usage of water, and use heat and only heat to minimize the viscosity reduction of the equation of the mobility. And so when we have the permeability over a lower viscosity, that will improve the mobility as part of our enhanced oil recovery methods. So the economics in the lab scale is beautiful. It can be cheaper than the water, because if you, and I come to this conclusion, if you remove the water from the equation in the EOR, you will have a cheaper technology. So dealing with water and the environment of the chemicals and the media of the solutions that you are going to inject in your reservoir, that's going to add up to the cost. So as if you remove the element of water, things start to become cheaper. In a short comparison between the dry heat and steam, we found that the coal production give us between 1 to 10 recovery ratios. Maybe not economical for heavy oils, but for medium oils, coal production can become useful in the EOR business. The cyclic steam can get us between 15 to 30%, but we are going to have a nightmare dealing with produced water and the produced water issues. The SAGD is 40 to 60%, but we also have to deal a lot with the feedbacks or the flowbacks of the water issues produced. The electrical viscosity reduction, which is basically our technology, the Haddad, is 30 to 60%, and there is no water issues whatsoever. So that becomes very economical benefit. In the in situ upgrading and conventional, which basically if you continue adding heat, you reach to the condition of a refinery, basically. That was the idea. And you transfer the crude oil into diesel in situ, and you just produce diesel and you sell it and take it to your markets. It can reach in the lab, of course, up to 40 API crude oil. So if you have even a heavy crude oil, I dealt with a 17 and a 15 API crude oils. I managed to get them up to 40 APIs. The problem is you shock your reservoir with intense temperatures. As it cools off, it will become a different matter. So we still haven't figured out how we're gonna do when it starts to cool off. So I spent in the lab for this technology to talk about the benefits. We can put heat wherever we want it. It does not increase water cut. It reduces energy losses and the overburden, controllable, high temperature not dependent on pressure, no water to react with the formation, heat input tolerable in the horizontal section, can use renewable energy, possible demand response, all the good stuff. But in our business, we always look at the drawbacks. And the current situation and the current moments right now, the drawbacks is as follows. The electrical heater technology is still immature. The BTU energy equivalent cost is still higher than, let's say, the natural gas, the BTU that natural gas can provide us. Significant electrical generation capacity usually not available, and this factor is varied from a country to a country, to a company to a company, where you have the wattage is different from company to company, region to region, country to country. So that cannot be standardized still. Most petroleum engineers are not familiar with the electrical engineering, products, designs, and options. Actually, if you want to go after this technology, you need electrical engineers. They can give you a lot of benefits and cut corners in the energy consumption and the efficiency of the equipments that you are going to use. So we move on to the next subject, which is the new technology of the low salinity water flooding. Some people call it LS water. What it does is we are dealing with the molecular level of what's happening between the reservoir and the fluids there and the fluids that we are going to inject. So we can go and deal with fine migration. This is going to help us design better materials or additives to that water, let's say nanomaterials. Also the saponifications and the ion exchange, the mineral dissolutions. All this is at a molecular level, I would say, at the angstrom to the nano up to the micrometer level of physics that we need to understand. So it is an enhanced oil recovery method that uses water with a low concentration of dissolved salts as the flooding medium. But today, the natural sources of these low salinity are rivers, lakes, or aquifers. So even this is not a very attractive choice in the Middle East, in the middle of the desert. However, it depends on your definition of a low salinity. If you deal with a reservoir, aquifer, or effluent water with the crude oil, seawater can be a low sal. Anything with a less salinity, brackish water can be a low sal. You can design, you can mix, you can filter. So there is, it's the boundary of this definition is not defined yet. So how does it work? There are many mechanisms. Unfortunately, we don't know which one is more dominant than the other. Fine migrations, that's by Tangamoro, saponification, reduction of the interfacial tension, multi-component ion exchange, double layer expansion, mineral dissolution, desorption of organic material from the clay surface, and the electrostatic attraction reduction between oil and clay's edges. All these good stuff, we don't really know how it's interact by themselves and with each other. However, they all have the same end result, which is altering the wettability and lowering it and making it more toward the water wet, which that's what we like it in the EOR. Some companies around the world, they call it low sal, others call it design water, some call it smart water, others call it advanced ion management, others call it ion tune water. The truth to the matter, they are all the low sal technology. It was observed in a high oil recovery than many other techniques. And it is very simple. It's just water and you add it to your reservoir. It is low salinity and it will increase your recovery. The technology has been there for 15 years. The low salinity water flooding is environmentally friendly or friendlier than other techniques, and it's a cost-effective method. The only challenge or the true challenge is this, the availability of this medium, of this low sal medium. So it can unlock up to 30%, or it gives you, in my lab, I managed to get close to 27% more recovery than other techniques. And there are many factors remain unrecovered in the oil reservoir, such as the energy depletion, the heterogeneity of the residual oil, the high viscosity of the crude oil, if there is a fracture, oil wet reservoirs. So what this technology is bringing everybody is it can adapt all other EOR techniques to the table, which makes it very interesting in designing purposely built injection water for recovering EOR crude oils. And we can amalgamate it with chemical, thermal, and gas injection techniques. We found that it is a low cost and it can increase the oil recovery. And this is with my students. We found out that we could have increased the recovery in a substantial, like 27% recovery in the lab. Low salinity water flooding differ from normal water flooding in the ionic composition. So in the essence of this water, it can react with the fluids themselves and with the reservoir minerals to increase the recovery in the form of wettability alteration. Right now we are comparing, and we have what we call recipes for the smart water, and the recipes are endless. Here we have 7, and we have just a plain low salinity water. We injected toward the end of actually secondary recovery program, and we have a WAG, and then low salinity water, and then we have low salinity, and then alternating with the surfactant, and we have foam, and followed by LS, alkaline LS water, then foam, surfactant, water, polymer. The idea here is order. The sequence is important. Which one comes before the other in order to maximize the wettability alteration. We have a wettability alteration up to 40%, which is a good news for us in the EOR. We also found out that the polymer, we inject polymer and then we inject, following the LS water, is far much displacing and increase the efficiency much better. There are, as I said, endless recipes that we can do. The order of these injection is what makes it higher recovery. So if you want to maximize your EOR, you better pay attention on the sequence of which treatment comes before what. Toward the end, I would like to explain also the last and the third, the last phenomena, which is the wettability phenomena in the EOR study. A lot of people don't give it a lot of thought, but wettability is a complex phenomenon. For it is too difficult to yield accurate measurements and control of a quantitative repeatability or a short time of experiment that we don't have the patience for or the money to go after. So captured rock physics is important, and deterministically reported as a big morphological, and that's my approach, is through imaging rather than the conventional technique. Digital technology gives us a new physics, so we need to explore the new physics of wettability. And hopefully I can do this in 2 or 3 slides. These study objectives are to accurately measure wettability. The conventional wisdom right now only deals with 1D wettability. I did a lot of experimentation in the 2D. The ultimate goal or target is the 3D. And to be fair, I found out that the 2D is far more information discovery than the 1D or the 3D. We are trying to understand the the wettability in the pore geometries. And my case here was a heavy oil silty sandstone. It is important also to know that the contact angle is poorly understood and not measured in a conventional labs. A lot of labs gives you a lot of numbers, but there are no standardization. So basically, we like to refer to the wettability phenomena as the fat elephant in the room that nobody wants to talk about. It's always there, but no, they are treated as it's invisible and nobody wants to talk about it. So they usually go by empirical formula, partial models, derived equation, theory from the literature that's far from the real condition of your reservoirs. And what I did basically is to have a new classification that I could capture it significantly and very clearly. And I will try to make it into 6. I found 9, but I can summarize it into 6, which is a strongly water wet, SWW, medium water wet, and medium oil wet, and strongly oil wet. Waterability in real reservoir rocks is a condition value estimate rather than a single value. So most of the conventional wisdom will give you a value of the waterability as a single value. To me, waterability is like a porosity. It's like saturation. It's a distribution. It's not a single value. And we need to understand that. It's part of the new physics. Introduce waterability contact angle, the mirror effect, because we are dealing with 2D. We managed to measure from 0 to 360 degrees angles, contact angles. So we refer to it as a mirror effect. We're going to discuss it. And all reservoirs have their signature 9 contact angle classification, but different proportion. And that's what makes each reservoir unique and different than the next door reservoir, the next door neighbor reservoirs. So as you see here in the top sketch, this is the 1D, the conventional conceptual models that everybody has studied, which we have an oil wet system, water wet system. The contact angle, if it is above 90 degrees, that's an oil wet. Less than 90 degrees, that's water wet. Unfortunately, this does not happen inside the reservoir. This is only on smooth surfaces that is not talking to your reservoir. It's far from your reservoir. The reservoir waterability is complex. That's why it's part of the being the big elephant in the room that nobody wants to talk about, is the conceptual is actually pretty old. We need a new physics. We need new models. We need to go in that avenues. So let's say we have here a silty sandstone. We have clays, we have silt, we have sand. Here in the first model, we only have one, the whole reservoir are represented by one mineral, either sandstone quartz or carbonate calcite or dolomite, like that. Truth to the matter, the reservoir is more complex. So we have more minerals affecting to your waterability and contributing. So if we transform this to this picture here, so this only one pore, we found there is about 11 different mineral grain walls, and they are all contributing to the waterability. So the waterability in this pore space is actually a collective effort between 11 minerals, plus your water, plus your gas, plus your crude oil, and plus your chemicals that you want to inject. So I think it's time now to move to a more realistic models or conceptual models. So here, what we found is, thanks to the digital technology, we found all kind of pores. So if we have one pore that has 11 surfaces, and if we have, let's say in this image, 10,000 pores, amazing. So the distribution. So right now we could measure in the lab the amount of pores and their waterability in a big data format, that's also what we like it for modeling. So what we found that there is between 1 to 6, there is a strong water wet, SWW, and that's from 0 to 30 degrees. The medium from 30 to 60. The weak water is 60 to 90. The weak oil wet is 90 to 120. The medium oil wet is 120 to 125. And the strong oil wet is 6. And then we have a mirror here, and that duplicate the angles in the other matter. So what we found in this classification, each EOR treatment can be successful in one of these regions. So let's have here, if this is the 0 and this is 180, from 0 to 30, this blue here, SWW, this is actually strong water wet, which means that's your primary recovery. So 30 to 60 is the medium water wet, and basically that's where your window of operation of your secondary recovery, which is water flooding, regular water flooding. The weak water wet is where the surfactant is going and working. And after the 90, we start to introduce the temperature, and we're going to talk about it. Here we have this mirror. So this is where we think from 0 to 30 and from 300 to 30 to 360, this is the primary recovery. So now we can tell you that your reservoir, by the way, all reservoirs have the same distributions, but with different frequency and availability. Some reservoirs have more 0 to 30 than others, and so forth. So from this analysis here, we found out that what is your maximum theoretical limits that EOR can work. In my study, I gave only 6, which is the 0 to 30. There are reasons I excluded, and that's what we need to have a future. We need chemicals to improve the wettability that works for the 0 degrees, something that we could not even measure in the lab before, and the 90 and the 180. So here, what we learn that the cold EOR is from 0 to the 90. After 90 degrees, there are pores in your systems needed temperature. So if you have thinking of thermal treatments, think about what is your target. Are you going to lock this oil or that oil or this oil? Because these oils can be recovered without even introducing any temperature. But how much? And by the way, as we go here, we are increasing. So we should expect that the secondary recovery is more expensive than the primary recovery, and the surfactant is more than the secondary, and until we get to this region here, that's the most expensive oil to get out. We found out that primary recovery is 0 to 30, secondary 30 to 60, chemical flooding with low heat, all right, low sal, smart water with heat between 100 to 300. This is the 120 to 150 degrees angles, contact angles, unconventional treatments, high temperature, and so forth. What we found out are that all reservoirs have mixed wettability, which is like that, all reservoirs. So, but the differentiation between each pore classes and their degrees varies from a reservoir to a reservoir. In this case study, we found that the primary is about 12%. That's the maximum recovery. And the secondary is only 14%, adding to the primary. The low salinity can improve it to about 19%. Chemical flooding can give us 25, but at what cost? Smart water, 17, and the unconventional treatment is 11. So the last slide I have for you today is to give you a roadmap about the solution that you need to do in your EOR, which is there are solutions that needs spotting, and these are have the tendency to have 7 times more success, like the hot air, the Haddad, but again, that's in the lab. Smart waters, nanofluids, heat management, acid treatment, surfactant treatments, water separation, and all these good stuff that can go with the smart water, low sal. Digital transformation, new chemicals, all this is a solution that needs spotting right now. Mental invention, it has 3 times more failure, but if it works really nice. This kind of actually solution requires money, which is not a good solution in today's economy. This is the fluid composition. We found out that carbon, hydrogen, nitrogen, sulfur, oxygen is very important mix that's gonna be unlocking the EOR crude oils. The NSO, it has heaviness and it will resist getting out to the surface, while what we need is carbon and hydrogen, which is the hydrocarbon. So we need to understand more the compositions. And the second is the economy. Each EOR should have an energy loss, energy gain equation thrown into the development of this EOR techniques. Need spotting, which is have 2 times as many success as failure, but it's doable, is the artificial intelligence solution, new platforms, iClouds that can speed up decision-making. Scaling up, we need also to address it for EOR projects. The project life cycle, what we found that EOR cycles usually takes longer time. It needs to be shortened. I believe 2.5 years should be the maximum cycle of that project. So if there is any complication, it needs to be reduced and handled and attended to it quickly and shorten the project life cycle, because aborting a life cycle can happen at any minute in the EOR project. Random events, crude oil transfer. I was thinking that instead of having the tankers, which takes longer time to reach to the market, maybe we can propose transferring the crude oil, the EOR crude oils, by air freight. Insitu upgrading, we can get diesel for you, syngas, gases from the crude oil without having to get it to the surface and deal with it and take it to the refinery and transport it. Maybe that can also have a good return on us, and also the nanoparticle materials. With that, I'll be very happy to answer any question. I hope I didn't take too much of your time. Thank you for listening.
Thank you very much. Really appreciate it today, presenters, and I will invite all our presenters to open your cam, and please let's start our panel discussion term. Really appreciate it. Sorry for the inconvenience related into the transmission and the videos, but that is something that today technology challenged us, but as well allow us technology to be connected today around 50 people from all over the world together here on this matter. Thank you, Dr. Khalid. And let's welcome, please, to open your cameras, and let's start with our first questions about how we can integrate it. Thank you, Gisela. Hi, nice to see you.
Good to see you too, Cesar.
Thank you. Dr. Khalid, are you around? We can start your camera. Appreciate it. The same, Dr. Chan Liu, Professor Riji Lin, and Dr. Himanshu Sharma, and Johnny Fang. Thank you very much. Okay, let's start with that. I get some questions, Gisela. People is asking into the chat, what do you think about today's challenge about the resolutions and the scale, how we interact in our simulators with the different scales as we need to go in higher resolutions. So how we can improve it? And this is a question to all the presenters. So let's start with you, Gisela. Thank you for opening your cam.
Thanks. Precisely, the work started with this question, and the reasoning for having the small grading so fine, it was based on the size that we do core flooring in. So the 30 centimeters is the normal core floor length we are using. And normally the diameter is 3 centimeters, but the geomodeler couldn't go that small because of the log resolution, and 6 centimeters was the smallest we could handle. However, you know, the real resolution from logs is between 15 and 50 centimeters, which is what we use in the real field scale models. The issue is the computing power, because the smaller you go, the more power you need. However, the EOR processes require more and more definition than conventional water flooring. So I think it's a big challenge, but it's something we need to consider in order to predict properly the incremental oil.
Thank you, Gisela. And another speaker that is connected would like to add something to what Gisela said. Okay, looks like people getting some issues with the microphone or the video. Maybe we can ask Liz or Nora, our speakers, to open the cam and the microphone. Maybe they have some issues to connect it. Thank you. Let's move forward to other questions related to, in the case for Gisela, how we can, the multi-layer conditions from the reservoir be considered, as you say, about particle sizes once, but as well multi-layers options related to the consideration of the reservoir and fabric conditions.
I don't follow the question well.
Yeah, the question was related from Yesenia Soto, how the multi-layer reservoir can be simulated. Maybe Yesenia, if you want to raise the question.
I think the question was not for me.
Okay, sorry, I was thinking it was for all.
Basically, I can go back to the issue and why we are upscaling, and maybe this might answer both questions. There was a question on why the sensile impacts the incremental oil. So it's easier to understand why it impacts the way the tracer displacement is modeled, but not the incremental oil. And the answer for this is there is a combination on the reservoir heterogeneity and numerical dispersion. And the thing is, every time we upscale, we are generating a different degree of heterogeneity. And if we compare on the same grid size, the 100 realizations, for example, each realization yields a different incremental oil. And the moment you increase the cell size, you are generating a new realization, is a new amount of sand interconnected, and also basically it homogenizes the models. So basically, to answer both questions, the issue also with the multi-layering is like the more layers you have, the smaller you need to go in order to capture the effect of this heterogeneity in the EOR process.
Thank you, Gisela. Appreciate it. Dr. Sharma, are you around? Liz, I don't know, maybe the other speakers have some issues with the microphone or the video. Okay. Okay, thank you, Gisela. No, thank you all of you. Have been getting a lot of comments about it. Thank you for amazing presentations. Thanks for the presentations. As well, some questions will be sent as well to the speakers. For some of the hemispheres, it's quite late in the night. So we will see how we can put it together, and we will send you the answer to your questions through via email to you. Gisela, any comments about it? What do you think about the overview we have today from conventional and unconventional, the different reactions we have it, the different process on thermal, chemical conditions? What do you think about it?
It was a very nice and comprehensive set of presentations. I think they covered pretty much what we are interested in the company or in Austria. Wettability alteration, it's a key, especially for carbonate reservoirs. So it was a very interesting talk about it. And I think the challenges are the same all over the world, but we have, of course, each region also comes with additional impediments or additional things to solve. But in overall, I think we're all interested in the same methods. Heavy oil is also very important in Romania for us. And there are years and years of experimenting in steam injection. And now we are also going with chemical for these same reservoirs, because we need to go one step further and increase the technology. We're also working a lot on nanoparticles. And I think this is another topic that opens many challenges, starting from not only from the resolution, but also how the wettability alteration is happening, because we're talking about a completely different scale. And I think it's also interesting the new applications when we're talking about carbon capture and geothermal. So I think it was a very broad morning session. And I think we covered a bit of the current fronts we are working in EOR in the industry right now. If you like, I would like to answer a few of the questions if we have time. So yes, very quickly, it was asked which sort of tracers we use. Normally we use non-reactive conservative tracers. Basically, the most used is FBA or fluorobenzoic acids. And in the model, what we are injecting is a small slug size. It's about 0.1 per volume. So it's only pulses of the tracer, and then we're seeing the response. And it's very interesting going back to the multi-layer effect, because we always get multiple peaks for the tracers. And with this study, I didn't present these results, but we addressed this, and we found out that in order to get all those peaks, you need to go very fine in the grid size. When you go up to 5 already, you will always only see one peak, which is combining the effect of all these layers together. And regarding the formulation, how we come to this formulation is presenting in a SPE paper, but it was a combination of the phase experiments, micro models, and core float results. And in the model, we are using 1 per volume, which is what we expect to inject in the field. But we don't have an optimized slug size yet. And I think those are all the questions.
Okay, thank you. Thank you, Dr. Khalid, for being here. They had some questions as well to you. Thank you, Gisela. people ask it a great lecture. Dr. Khalid had been thoughtful, and I enjoyed it. People enjoyed it about. The question is, knowing that EOR is abroad, how can people specialize in a specific area of EOR? What would be your advice?
I think it's a combination of petroleum. I mean, petroleum engineering is a must, but you have to be integrated with other engineering and other skills. We don't want just a petroleum engineer full of ideas, full of enthusiasm. We want somebody with the skills, somebody who knows a little bit electrical engineering, or a minor in electrical engineering, or a minor in artificial intelligence. Faster computational skills is always needed for EOR. So we want our engineers or our researchers to have been skilled with computational, whether it's in artificial intelligence. Right now, simulation is something of the past. So we need something that it's been trained. So we don't have the time, because EOR is always a function of time. We have to do things faster. Otherwise, we cannot compete with the other trains. So we need always the element of speed in computational, speed in doing. So we need automations, we need robotics, we need faster intellectual skills in the computational as well as in the physics. In that regards, I think the best combination will be a petroleum engineer plus a physicist plus a mathematician and an electrical mechanical engineer, or if we combine them together as robotics engineering. I hope I answered your question.
Sure. Thank you, Dr. Khalid.
Yeah.
Really appreciate it. And in the current in situ reactions, how you see we can improve and apply energy efficiency and include renewables on it?
Okay. If we increase the materials of the conduction, like for example, we can use nano copper, nano cobalt, anything with the heat induction that retain the heat inside your reservoir and does not lose it quickly. Or if you have a new material, as I said before, purposely built, unfortunately, there aren't people are working in that avenue. So that technology is still in a trial and it's immature. We need something that when you pass the electrical current, it immediately transfers it into heat and stays there for a long period of time, does not lose it. In the lab, I worked with cobalt and I worked with copper and I worked with the stainless steel. The copper was by far the best. So if we need to invent or come up with a new material, let's say a hybrid between cobalt, but has to be cheap. Graphite has a future if we know how to do the nanotubes and the nano graphite tubes. Maybe it will retain even further heat with less energy. I hope I answered your question.
Yes, sure. Thank you. And definitely include nanoparticles and work on how we integrate these new materials is something that we put efficiency and how we come on that one. Thank you, Dr. Khalid. Thank you very much. Dr. Lin Ri, you asked me to please, Dr. Lucian is going to help us with the questions related to you. Thank you. Okay. Thank you. There are people on the chat have been asking, there is no values related to oxygen. The oxygen quantity values are very important to have into the aromatic rings as they are combined with nitrogen and sulfur. Any consideration related to oxygen? Thank you.
Yeah, thank you for the question. Firstly, actually the content of oxygen in the oil sample is very small. The firstly, and secondly, the disulfide macromolecules undergoes an enolization reaction and generates a carbonyl group, and then continue to cleavage to carbon monoxide and methylene. Part of the carbon methylene will undergo water gas conversion reaction in the presence of water. So finally generate some carbon dioxide. So because the generation of carbon monoxide and carbon dioxide, we cannot detect oxygen elements in the oil sample in the end, or there is still little content of oxygen remain in the oil sample, but is an undetectable level. So there is no oxygen shown in the table. That table, I think. Yeah, that's the answer. Hopefully, can answer the question.
Yes, sure. Thank you. People asking as well about the size of the particle of the catalyst used. What do you think about it, and any comments about it? Thank you.
The particle size we use in our experiment is, I think, actually the active part or active site is in a nanoscale. For the entire catalyst is 40 to 50 mesh size, which is about 300 to 400 micrometer. But actually, the molecular size, the molecular size is arbitrary because it can be green or screened, depends on the design. Yeah, that's it.
Thank you very
Another
much.
Question?
Yes, how this can be used into a multi-layer reservoir?
Okay, I skipped two questions. Sorry, I think I skipped two questions. I will answer them first. Okay, I'm sorry.
No problem.
Yeah, there's another question. Yeah, the chemical nature of catalyst. Yes, thank you for the question of Medina, right? Dr.
Oscar
Medina.
Medina, yes.
Yeah. Because we have a confidential agreement, so we can tell the detail or specific recipe of our catalyst. I'm sorry for that question. Another one is to upscale the application. For sure, we also looking forward for the application of our catalyst in the field, but still it's in the lab stage at present. Yeah.
Thank you, Dr. Luchan.
That's
there is a question. Another one is about pressure drop in the scaling process. Pressure drop into that scaling process. How you measure it?
Sorry, the question? I didn't follow the.
Yeah, it just pop up a last question for you, and is one about pressure drop in the upscaling process.
A pressure drop?
Yep.
Oh, I didn't follow the question. It's related to my research.
Oscar, you would like to
about pressure drop. Oh, okay. Another question. Yeah.
Yes.
No. We do not have that. We haven't measured it. It's still in the experiment stage. So for the upscaling one, we haven't do the research.
Okay, thank you for that. Thank you, Dr. Luchan and Lin Riji for that. There are some questions for Dr. Sharma, and other questions come into the chat. Thank you all of you. We will pass then. Maybe they had some issues with the mic. on the questions, but I will ask them by mail, and I will check with all of you. We go for a 5-minute break, and then we come back with our next panel sessions. Thank you, Gisela. Thank you, Dr. Khalid. Thank you, Lucian. I know it's quite late or early in the morning there to be here connected. So really appreciate it. Thank you.
It's midnight here. Thank you.
Thank you. Bye-bye.
Thank you. Okay, and for the people who have been already just connected, we already have been going through the different options on in situ reactions. We start, appreciate your attendance. We are going to do a break of 5 minutes and come back with our next conference. Thank you very much, appreciate it.
Energy security and sustainability begins with global collaboration. This was the belief that led to the creation of a technology collaboration program just 1 year after the IEA was created 45 years ago. The TCP provides the IEA with a unique technology network unmatched by other international organizations. It is global and is open to IEA members as well as non-member countries. It cuts across energy technologies and topics such as energy efficiency, renewables, fusion power, hydrogen, and fossil fuels. It is an essential forum for governments and industry to work together and focus on the most challenging energy issues of the day. TCPs have pioneered the development of cutting-edge technology, including smart grids and wind turbine blades. Their work informs the IEA analysis as we look to shape a more secure and sustainable energy future for all.
Thank you. Let's continue now after our first break. Let's continue with our next talk. I would like to introduce Dr. Berna Haskell here, Associate Professor. We're going to be with her on the carbon dioxide fluorine for heavy oil recovery, how to maintain miscibility as important reservoir asset we have today. Dr. Berna, good morning. Really appreciate it. Dr. Berna Haskar is an associate professor of the petroleum engineer, a flow-tech industry and career development professor as the director of the heavy oil, oil shales, oil sands, and carbonate analysis and recovery methods research team at Texas A&M University. She holds a bachelor's degree, a master's degree from environmental engineering, and PhD degree from petroleum and natural gas engineering. She pursued postdoctoral studies at Stanford University in the energy resources as part of work as well on the resource engineering department, and worked for Schlumberger Venezuela, UK, and Colombia, a senior heavy oil reservoir engineer, more than 150 publications, and a distinguished member of the SPE, and a good friend from the house. Thank you, Dr. Berna, for being here today with us, and really appreciate it to have you here today.
So thanks a lot for the invitation, and thanks a lot for the introduction. I'm working for A&M around 10 years, and my research expertise is all about the dirty portion of the oil, which is heavy oil, and the cleaning of the dirty portion. I'm also doing some produced water management. I'm interested in also the carbon emissions. I have some publications on carbon emissions as well, because we need petroleum. We all know that. And while we are producing petroleum, we can be considering the environmental factors more. But in this talk, I will be concentrating on one of the EOR topic, which is miscible flooding. And I am planning to get rid of carbon dioxide because of its greenhouse emission effect. And I know that I'm a heavy oil guy. I know that carbon dioxide is not miscible in heavy oil. And if I would like to be if I would like to do an EOR process, and if carbon dioxide is immiscible in the heavy oil, then I can do immiscible flooding, but not miscible flooding. So now I would like to just concentrate on how I can make carbon dioxide miscible in the heavy oil in my talk. So this is a really simple representation to explain what is miscibility. As you can see here, we are mixing coffee and milk, and they are getting 100% miscible, and there's no return back. Okay, so we just made it miscible completely. And this is what we would like to maintain as well for the carbon dioxide and heavy oil. And what is, in order to understand digest miscibility better, we need to understand also what is immiscible. So here you are seeing two phases, two different components at the same phases. Oil is liquid, water is liquid, but they are not miscible. But here we are talking about carbon dioxide in gas phase, and heavy oil is in liquid phase, and we would like to discuss gas and liquid miscibility and how we can maintain gas and liquid miscibility. So here I have in the oil multi-component. Okay, I don't have just one component in the oil, but here in the water, I'm assuming that I have just water, one single component. So this is a multi-component system, but single phase. Still, it's not miscible. And I'm interested in carbon dioxide miscibility. And why carbon dioxide? I'm a petroleum engineer, and I hate to just mention climate change, but it is reality. We all have to accept it, and it is scientifically proven. And we are scientists, so what we need to do, we need to bring a solution to this one, because it will bring our end, all of ours end. So what we are seeing here in this picture, we are seeing that the temperature of Earth is getting increased steadily. And when we check the atmospheric level of the carbon dioxide level in the atmosphere, we are seeing it is also increasing steadily. And they are correlating, which means that we release carbon and carbon dioxide, and it is turning out a kind of a greenhouse gas, and it is making the Earth's surface heated more. So I would like to just go about the daily life example of the carbon dioxide. And I'm trying to get rid of carbon dioxide because it is a bad guy. It is causing global warming, climate change. And I need to understand more about carbon dioxide miscibility, because we are, as petroleum engineers, are the guys who are using carbon dioxide most. Actually, the reason why we have carbon dioxide in the atmosphere is because all of us, not only petroleum engineers, but all of us are consuming fossil fuel. But who is getting rid of that carbon dioxide most is, again, us, petroleum engineers, because we are using it as an enhanced oil recovery fluid or any other recovery fluids. And if you would like to sequester also carbon dioxide, the knowledge is coming from the petroleum engineering experience again. That's why I would like to, as a petroleum engineer, know more about the miscibility, because I would like to inject more carbon dioxide to recover more oil. If I will not maintain miscibility, then I will recover less oil with the same amount of carbon dioxide. So this daily life example is helping me to understand the miscibility really very well. So here you are seeing a can, soda can, and it is closed, which means that it is under pressure. And while it's under pressure, carbon dioxide bubbles are dissolved inside this soda. And then once we release the pressure by opening the can, what's happening? Because of this pressure release, because I'm changing the pressure of the system, then carbon dioxide starts to release. So this is my reservoir, actually. If I have enough pressure in the reservoir, I can maintain the miscibility of carbon dioxide in the reservoir. But if the reservoir pressure will be around atmospheric, then I will not maintain the miscibility, and then it would be immiscible flooding, not miscible flooding, that I will maintain with carbon dioxide. So this is all about pressure, temperature, and compositional change. So it is just dragging me to a PVT diagram. Okay, so this is my PT diagram for carbon dioxide and the pressure and temperature. And I'm interested in this line most of the time, and this line is called vapor pressure line for carbon dioxide. Above vapor pressure line, I am in the liquid zone for carbon dioxide. Below, I'm in the gas phase, vapor phase of the carbon dioxide. But on top of it, I have two phases. When I have the two phases of the carbon dioxide for single component system, just carbon dioxide, even for just carbon dioxide, I cannot maintain miscibility. We are interested in mostly supercritical region, but I will come to that point later. And here another daily life example of one component system, but not miscible again. Vapor water and liquid water. They are just single component, but they are not miscible, okay? Because I'm seeing two different phases here. I am not interested in miscibility, two different phases. And I'm not talking about single component system like carbon dioxide, like water, but I am interested in multi-component system, because I am injecting this carbon dioxide to heavy oil reservoir. Heavy oil is already multi-component, and I'm adding one more component. And in the reservoir also I have water, reservoir water, another component. So things are getting really complicated. And how I can explain the miscibility for multi-component systems by using some other diagrams. Again, you are seeing here pressure temperature diagram, and this is composition diagram only at constant pressure and temperature. Phase behavior is really complicated. It is not straightforward to understand. And these envelopes here you are seeing are just showing me two phase region that I need to be avoiding. Okay, so if the composition of these components in the reservoir are falling into this two-phase region, then I cannot maintain first contact miscible processes. And here you are seeing two component system blends. Let's say here I have methane vapor pressure line, ethane, propane, and it is going till decane. And I would like to let's say my reservoir is a decane reservoir, normal decane reservoir, and I would like to recover this reservoir by injecting methane, and I would like to do it as an EOR method, miscibility. Okay, I would like to maintain. In order, if I would like to just inject methane to decaying reservoir, this is my phase envelope. In order to maintain miscibility, I need to be away from this region, which means that I need to increase the reservoir pressure or reservoir temperature really a lot to maintain miscibility to avoid this region. When I'm checking for carbon dioxide, what I'm seeing, carbon dioxide is much more reasonable than methane, but still my envelope is still so big, as you can see. This is for carbon dioxide envelope as the kind of a phase behavior, but a multi-component system. This is two-component system. And the methane is giving a bigger phase envelope, which means that I cannot maintain miscibility. Okay, it is much more difficult to maintain miscibility with methane other than carbon dioxide. So if I will insist to use methane, it is really difficult to do an enhanced oil recovery, but carbon dioxide is much more promising. So what we talk about till now, we talk about single component system cannot be even miscible because they may have two different phases, vapor water and liquid water. And we also talk about multi-component system, and in the multi-component system, I may have the mixture in the gas phase and the mixture in the liquid phase. And because of this mixture in the liquid phase and the gas phase region exists, so I may not maintain miscibility if I'm not staying out from this two-phase envelope region. And what else? I talk about gas phase, I talk about liquid phase, and I am looking for single phase. Either gas phase it will be or liquid phase. Do I have any other phases that I need to be concerning? Yes, we have one more concern, and this is solid phase. And the solid phase is my asphaltane. And what is actually asphaltanes? Asphaltanes are insoluble in normal alkanes, but soluble in aromatic solvents, and asphaltanes are part of crude oil. And this solid phase is distributed inside the crude oil, either in dissolved form or dispersed form. Okay, and once we are changing the dynamics of the system, once you're changing the pressure, once you're changing the temperature of the system, what's happening actually? You are precipitating asphaltanes. Okay, you are precipitating the solid phase. So this is very important that we need to understand that we don't want also another phase in the reservoir, in the pipelines, near wellbore. And what I am seeing here, if I'm adding to the reservoir a solvent called normal alkane, then I may precipitate asphaltanes. And different normal alkanes is just resulting in different amount of asphaltane precipitation. So, and here you are seeing N-pentane and N-heptane asphaltanes. So with the change in the carbon number in the in the alkanes, I am getting precipitating different asphaltanes. And the different crude oils, these are all three different crude oils responding differently to those insoluble solvents. And this, what I'm telling here, not only normal alkanes, but also carbon dioxide is insoluble in asphaltane. That's why I have a problem here. If I would like to inject carbon dioxide into heavy oil reservoir, I will create gas and liquid phase, but these are not only two phases. I have also solid phase. I may have solid phase precipitated either inside the reservoir if I can maintain carbon dioxide distribution in the reservoir, or I may have asphaltane deposition near wellbore or in the pipeline. Okay, why? Because not only composition is changing here in the near wellbore, I am seeing the biggest pressure change in the near wellbore, and I know that the phase change is happening when I'm changing pressure, temperature, and the composition. By adding carbon dioxide, I'm changing the composition. And what else I am doing? I am also changing the pressure at the near wellbore. And this change is really a big change. And because of this change, I'm causing asphaltene precipitation. I may cause asphaltene precipitation in the near wellbore, and this will be enhanced with the presence of carbon dioxide. So now I would like to just go through, right now you are seeing behind my laboratory picture. So we are able to do almost every enhanced oil recovery process in my laboratory, plus all thermal enhanced oil recovery processes, including electromagnetic heating as well, the crazy ones, in situ combustion. And I have heard that Romania examples. So I had a chance to work in Suplacu de Barracu in situ combustion project when I was at Stanford and in Colombia. I continue to work on that. So here you are seeing the laboratory setup, and it's just located actually here somewhere at the back of me. And you are seeing here the steam generator. You are seeing here the core holder where we are packing any reservoir sample. And this is my small scale, lab scale laboratory setup. And then you are seeing here my steam generator, a lab scale steam generator, but we are able to go really high temperatures and high pressures with the steam generator. And you're seeing here my injection solvent, which is carbon dioxide actually, this one. And we are regulating everything about carbon dioxide with these regulators. And I have the production vessels. We are calling them separators. And in this summary, I would like to just mention that till now, we had a chance to work with lots of oils from all around the world. And you are seeing the locations of those oils, and you are seeing how they look like. They are nesty. And here the H stands for heavy oil. EH stands for extra heavy oil. B stands for bitumen. W stands for wax. So what is heavy oil? Heavy oil is, we are defining heavy oil as the API gravity more than 10, and we are measuring API gravity at standard condition, and less than 23 around. And the viscosity at reservoir condition, not at surface condition, at reservoir condition should not exceed 10,000 centipoise. So let's say reservoir condition here and reservoir condition here are totally two different reservoir conditions. Canada is really cold here. We have warmer reservoirs. And then what else we have? We have extra heavy oil. Extra heavy oil means that any oil heavier than water in terms of API gravity. So, and then we have also bitumen resources. We are not looking into API gravity while we are calling it bitumen, and anything at reservoir condition is having a viscosity over 10,000 centipoise, regardless their API gravity, is called bitumen. And the wax means that it is just like candle that you have at your home. Even you can touch the candle and you can see that the viscosity is getting reduced immediately with your body temperature. And wax means that it is mainly containing light hydrocarbons and saturated hydrocarbons, not light hydrocarbons, saturated hydrocarbons but C10, C20, C30, but these are mainly normal alkanes actually. And you are seeing also the viscosities, and they are saturated aromatics, resins, and asphaltanes amounts actually. And the asphaltanes are really difficult to determine. That's why we are presenting here two different asphaltanes, N-pentane and heptane asphaltanes. So I will not show all of it, but we have done a lot of miscibility processes on all of these oil samples, and you can find from my publications if you are interested in more. Now I would like to just summarize some of the outcomes of some processes. Okay, first I would like to just summarize steam carbon dioxide processes. Here, what we have: initial sample before after we pack it inside the inside the core holder that I showed you. I'm sorry, my cat is just, I need 1 minute break. I will just leave her out. I'm coming back. I am sorry. It is their nap time, but she decided to just have some fun. I'm really sorry. I just get rid of my kids, but my cats is still around. I'm sorry, really. Anyway, so so this is my initial sample, and the initial sample is my bitumen from Canada. And this is based on the Canadian bitumen mixture existing in the reservoir. Just we prepare this mixture. And then what we have done, we just injected steam, we injected carbon dioxide, and we injected steam plus carbon dioxide to recover this oil. So this is my initial sample. What is happening afterwards? And you're seeing here the post-mortem pictures. Post-mortem pictures means that after the experiment, after we get the oil recovery, and then we are opening the reservoir, we have a chance to open the reservoir and look inside what happened. And what we have realized here, 32% oil recovery with steam flooding. Just with carbon dioxide flooding, I got 15%. And with carbon dioxide with steam, I got 41% oil recovery. So what's happening really here is the oil recovery mechanism is mainly convection, and steam is really helping and improving the oil recovery because this oil has an initial viscosity around 54,000 centipoise. And then I have here carbon dioxide flooding. As I mentioned before, carbon dioxide is immiscible with this oil. And it's because of the immiscibility, I just use like piston-like displacement here, and I couldn't recover that much. And this is just actually because of the pressure difference that I'm applying between the inlet and the outlet of the system. And when we come to carbon dioxide and steam, I am amazed that I have seen because of the in situ reactions happening during this process, steam and carbon dioxide are both in the vapor phase and they are moving together, and carbon dioxide can be a little bit also miscible inside the steam phase, and this is maintaining a better recovery. So I enhanced, actually from here to here, I enhanced the oil recovery. But this one is not a kind of enhanced oil recovery, it is immiscible flooding. But here to here, I enhanced, improved a lot. And what's the difference between these two? How can I see the benefit of this? Actually, from here to here, I'm injecting less steam. Steam is getting produced in the middle of nowhere, which means that you need to burn oil to generate electricity so you can heat it up your steam generator. And here you are using more steam, which means that you have more greenhouse gas emissions, but here you have less greenhouse gas emissions because you are adding in a stream something else to recover. Even at the same amount of oil, you can recover by less environmental footprint. Plus, you are injecting carbon dioxide to the reservoir, and it is a greener solution for sure. So let's check also the asphaltene concept. Okay, what we said, okay, my concern is eliminated a little bit. I have here two-phase gas and liquid
oil, and the gas phase carbon dioxide. Do I have any kind of like asphaltene? Here I'm seeing in the produced oil more asphaltenes. Okay, and then here I have in the produced oil less asphaltenes. Why? Because I precipitated the more asphaltene in the reservoir rock. Okay, because carbon dioxide is insoluble in crude oil. I recovered less oil, but this oil is better in terms of asphaltene content. I left behind more asphaltenes here. And when I'm looking here,
it enhanced more. I left behind more and more asphaltanes, even though the color is lighter, the postmortem. Actually, this postmortem has more asphaltanes than any of these two, because I'm producing less asphaltane, means that the remaining asphaltane is where it is left behind on the reservoir rock. Okay, and the other aspect is, if we are injecting steam, we cannot really think that the produced oil is 100% oil. It comes with water, and we are calling it water in oil emulsion. So also we checked the water content in terms of like understanding how the quality of this oil is changing. As you can see, the water content of the initial oil is this much, and I have also initial water saturation in the reservoir rock, and I'm injecting steam in this case, and I'm seeing a sware emulsion formation. So this oil, even though I'm recovering a lot, but it has a lot of water in it. And this one is not that much actually water when compared to this one, but it is less than what carbon dioxide flooding has, because we don't have any water injection. However, we have initial water saturation that we had in the reservoir rock while we are preparing our reservoir rock. And these are just steam and carbon dioxide. And what I said, I'm trying to maintain the miscibility of carbon dioxide inside the oil, and how I maintained it by co-injecting with steam. But I need to be aware of the asphaltane problem and the emulsion problem as well. I need to check this too. And then I need to decide if this is what I want. What else I can do? I may inject solvent with carbon dioxide to maintain miscibility. I know that carbon dioxide is not miscible with oil, heavy oil especially, but some solvents are miscible in heavy oil, and this solvent may also be miscible with carbon dioxide. If I can maintain miscibility in this too, and if I can maintain miscibility between solvent and the heavy oil, then I may have a chance to have miscible flooding. And to be able to do that, we co-inject lemonane with carbon dioxide. Lemonane is an environmentally friendly solvent, and it is citrus-based, and you can buy it from anywhere, and it is edible, okay? So this is not toxic. We have tested tons of different environmentally friendly solvents. I'm not showing all of them. I'm just showing the most successful one here. But we have tested some biodegradable different solvents, several different solvents, really tons of solvents, and we publish all of them as unsuccessful cases. So I'm just showing here one lemonade. And here we have two Californian oils. This is an extra heavy oil, and this is heavy oil from California. And you are seeing their viscosity with the black curve, initial viscosity, and their change with temperature. When we add to initial oil, lemonane, in the 1:500 ratio, so you are getting a kind of a viscosity like that. So it is for the extra heavy oil, lemonane is increasing the initial oil viscosity, but for this one, it's decreasing the initial oil viscosity. It is interesting. Then we decided to run core flood experiments despite we are getting this viscosity, different viscosity results. So this is the first oil, this is the second oil. And on this oil, which is extra heavy oil, we tested just carbon dioxide flooding over 1 week. 1 week carbon dioxide flooding experiment, and we got 0 oil recovery at the end of the 1 week. And then instead of carbon dioxide, we just injected lemonade, and we injected lemonane plus carbon dioxide, and this is what we have realized. With the lemonade, we got 38% oil recovery, and once we couple it with carbon dioxide, we got poorer oil recovery, unfortunately. And we tested actually carbon dioxide first and lemonade. We tested all different combinations actually, and I'm just showing here the interesting ones. And on this heavy oil, we tested just carbon dioxide flooding, not 0, but 11% oil recovery we obtain. And once we inject lemonane, 60%. Once we couple it lemonane with carbon dioxide, we obtain 76% oil recovery, amazing oil recovery we obtain. So I can just easily say that we didn't maintain miscibility here by injecting carbon dioxide, and we created another phase, carbon dioxide, which can easily break through inside this core, and it didn't help. So for the, here you are seeing no miscibility for sure, and these two are miscible processes actually. So we maintain for some oils with this solvent, which is lemonane, we could maintain carbon dioxide with carbon dioxide, still miscible process, and enhance the oil recovery. And I didn't mention anything about wettability, but in the previous presentation, I have seen that wettability case as well mentioned, so I would briefly go through it. This is from one of my lecture notes, and this is the enhanced oil recovery lecture note. You are seeing here silica surface and the calcite surface. Once you are changing the oil composition, the wettability is changing. Even the surfaces are the same, and these are smooth surfaces. As you can see, if we have more aromatic structures in the crude oil, silica surface may even behave like, sandstone may behave like wet, oil-wet surface. And now I would like to just show you some importance of the wettability. So this reservoir rock is prepared with sand and clay mixture, carbon dioxide flooding, and the carbon dioxide steam flooding. And I would like to show without clay and with clay experimental results. If I don't have clay in the reservoir rock, my oil recovery 15%. If I'm adding clay to my reservoir rock, I'm seeing a reduction in my recovery. And same for the carbon dioxide steam as well. As you can see that almost half of the oil cannot be produced. So wettability is really playing a very important role, even in the miscibility processes. And you can see here more clearly, this is another solvent. This is not carbon dioxide. This is an aromatic solvent that I'm 100% sure that it will clear the reservoir. And I have here sand, only sand. And at the end of the experiment, I'm sweeping everything. If I'm adding clay, a little bit, a different clay, this is kaolinite, I'm seeing 20% reduction in the oil production in the lab scale, and you cannot think about the field scale. And if I have another clay which has eyelite in it, a little bit eyelite, it is like 2% eyelite in it, then I'm seeing a great consolidation in the reservoir. Okay, so I'm sorry I took a lot of time. As concluding remarks, what I would say that carbon dioxide is insoluble in bitumen and heavy oils, but we can maintain the miscibility by using different solvents. So water is a universal solvent. Everybody likes water. It is cheap, abundant, available. And if we can just make it steam, maybe it can recover more oil, but we need to be very careful with the reservoir rock. And lemonane is another example that we can couple with carbon dioxide and maintain miscibility. And I didn't review really in depth the reservoir rock impact, but it has a significant impact. Even in the lab scale, we are seeing catastrophic differences in our results. And I didn't mention anything about reservoir water, and we prepared our reservoir water by using distilled water. So salt will make everything complicated because salt is interacting with asphaltanes as well. And I would like to acknowledge my team because my students are just generating all of those results at A&M University. And I would like to thank you for your attention. And I add something here new. This is the Turkish version of thanks. Okay, I'm Turkish. Thanks a lot for your attention.
Thank you, Verna. I really appreciated your presentations, and welcome. Teşekkürler. Teşekkürler?
Yes, teşekkürler.
Teşekkürler. Teşekkürler. Okay, thank you.
And I'm sorry for the cat.
No problem. Okay, there are a lot of questions into the chat. We will be coming into the different presentations, if you don't mind. And if you please can answer some of them to the chat, that will be excellent. And
sure.
Thank you, Dr. Berna,
sure.
to have all of you here connected today. And just remember to all our teams that we are here today sharing what we are doing in our webinars. We have Insitu reactions today, and we are going to have low water salinity fluorine on 29th of September. So welcome as well to be part of that one. We will send you the invitations and how we can put together the same amazing knowledge and how we are working as you have been seeing today. We will be focused straightforward on low water salinity fluorine in our next webinar. With that, I would like to say thank you to Dr. Berna, and let's continue with our next presenter.
Good morning, everyone. Our next presentation will be developed by Oscar Medina. Oscar is a petroleum engineer with an honorary degree from the National University of Colombia. Doctoral student in engineering, energy system and same university, and doctoral student in chemistry and the University of Granada, Spanish. Research and has more than 4 years of experience in nanotechnology applied to the oil and gas industry, synthesis and characterization of nanomaterials, EOR and EOR process. Author for more than 20 scientific articles, published a patent, a book chapter, and other international events. Many thanks, Oscar Medina, from beginning with the use today from your presentation. Thank you.
Hi, and good day to everyone. For me, it's an honor being here and have the opportunity to share with all of you the most recent advances of my doctoral thesis focused on the effect of the morphology and strong metal support interactions of nickel, palladium, and silver nanoparticles for the thermocatalytic oxidation of asphaltenes at different pressures. This work has been developed and completed in my faculty at the Universidad Nacional de Colombia and the Universidad de Granada. Well, asphaltenes are known as the heaviest fraction of crude oil. Because they are extremely polar and present high molecular weights, their proper removal is of significance to enhance crude oil production technologies. The injection of air or oxygen-rich gases is by far one of the most widespread methods used for producing heavy and extra-heavy crude oils. Nevertheless, limited by the combustion front stability and the efficiency of combustion, pyrolysis, and oxidation reactions, asphaltenes converts mainly into coke, and advanced strategies are needed to circumvent this problem. The catalytic oxidation of asphaltenes using nanoparticles is an attractive idea. Nanoparticles present several properties and can improve considerably the potential of the thermal methods to decompose the asphaltenes and produce gases with added value. However, the synthesized material tested was far from perfect, and the major shortcoming is the reduction of the asphaltene decomposition temperature, which in most cases it occurs at temperatures greater than 300 degrees Celsius. Well, with excellent catalytic properties including oxygen storage capacity, highly active redox property, and a versatile acid-base chemistry, ceria have been proposed to decompose the asphaltene molecules. It was demonstrated that the redox cycle was useful for asphaltene selectivity and conversion over amorphous ceria, and the regenerative capacity of the support allows a continuous asphaltene absorption and decomposition without affecting the performance of the material. Despite the satisfactory results, there are still limitations and challenges to overcome during these processes, since there is not a complete understanding on the oxidative thermocatalytic reaction of the asphaltenes at high pressure conditions. Hence, the shape dependence of Sura based on catalytic performance for decomposing asphaltenes is the main objective of this work. Further, this research studies exciting topics, including the effect of pressure on non-isothermal and isothermal heating of asphaltenes in the respective kinetic study. Until now, the design of these systems for the application has not been explored. In this research, 3 different nanoparticles with cubic, orthorhombic, and spherical morphologies were successfully synthesized for a simple hydrothermal method. The cubic nanoparticles were synthesized using potassium hydroxide and a serum nitride hexahydride salt precursor. The orthorhombic nanoparticles were synthesized using the same salt precursor and a polymer PVP in a water ethanol solution. Finally, the spherical nanoparticles were synthesized using the same salt precursor and the polymer in a solution with only water. On the other hand, the effect of the strong metal support interaction was assisted by doping the different Syrian nanoparticles with a couple of nickel and palladium in a mass fraction of 1% of each one. Well, as for the characterization of the nanoparticles, the size and morphology was validated through scanning electron microscopy and transmission electron microscopy. The chemical properties were measured by X-ray photoelectron spectroscopy, Raman spectroscopy, and X-ray diffraction. And finally, the surface area was measured by nitrogen absorption-desorption. Well, the nanoparticles absorption capacity for asphaltenes was studied by batch experiments. A stock solution containing 2000 parts per million of asphaltenes was diluted for obtaining solutions with different concentrations between 100 and 2000 parts per million. Nanoparticles were added in a 10:1 ratio of adsorbent mass to solution volume, and the mixtures were stirred at 300 revolutions per minute for 24 hours. The nanoparticles containing asphaltenes were separated by centrifugation, and the supernatant was analyzed in a UV-Vis spectrophotometer. The amount of the absorbed asphaltenes was determined by this mass balance. Well, finally, high-pressure thermogrammetric analysis were done to evaluate the catalytic capacity of the synthesized nanoparticles. Here were different variables analyzed. The pressure was varied between 0.084 and 6 megapascals. The non-isothermal heating was done at a heating ramp of 10 degrees Celsius per minute from 100 to 800 degrees Celsius, and the isothermal runs were executed at 170, 200, and 230 degrees Celsius. Insights about the kinetic of asphaltene oxidation were realized based on a feeding and order kinetic model. The effective activation energy is obtained from the slope through the plot of natural logarithm against 1 on temperature when 100 of the asphaltene consumption is reached. Well, as for the characterization of the nanoparticles, the morphology insights were validated. The diameter of the spherical nanoparticles was observed as 14 nanometers with a rough surface. The cubic nanoparticles present cubes with a smooth surface and an average size between 14 and 16 nanometers. As for the orthorhombic shapes, are observed with an average size of 20 nanometers, and the structures are highly agglomerated. As for the content of Syria, it increases in the order spherical, orthorhombic, and cubic. Meanwhile, the oxygen content follows the opposite way. As for the high-resolution transmission electron microscopy image, it reveals that the 111 crystal phase dominates the surface of the cubic nanoparticles with an interplanar space of 0.32 nanometers. This is the thermodynamically most stable crystal facet. The orthorhombic are enclosed by the 200 and 220 with an interplanar spacing of 0.27 and 0.19 nanometers respectively. For the X-ray diffraction results, it is observed that with the change in sphere shape, the lattice parameter is slightly affected, being higher for the cubic nanoparticles. Also, the crystallite size through the 1-1-1 duration increases in the order spherical, cubic, and orthorhombic stereo nanoparticles. Therefore, crystallinity follows the opposite trend. As for the Raman results, the concentrations of oxygen vacancies were calculated in terms of this ratio and increases in the order spherical, orthorhombic, and cubic. Also, for the doped materials, it was observed that the lattice parameter is reduced regarding the non-doped systems. The reduction of these parameters can be attributed to a portion of nickel and palladium ions may substitute the stereo 4+ in the stereo lattice and alter the unit cell parameter of support, since a relatively smaller radio is found for nickel 2+ and palladium 2+ than the stereo 4+. Also, the concentration of oxygen vacancies increased after the doping process due to the increase in the effect size by nickel and palladium ions. From the X-ray for electron spectroscopy results, it is noted that the oxygen ascribed to the surface to lattice oxygen radio increases in the order spherical, orthorhombic, cubic nanoparticles. Also, the content of the stereo 3+ ions increase in the same line, and the presence of these ions is a consequence of the oxygen vacancies formations, and it promotes the activation and promotion of the oxygen on the bulk and in the surface of the nanoparticles. Interestingly, the amount of the stereo 3+ ions increase with the nickel and palladium functionalization in all samples. The increase in the stereo 3+ proportion ranked as spherical lower than orthorhombic and lower than cubic may infer with the surface modification of oxygen vacancies after the metal loading. The oxygen results corroborate the hypothesis. The content of the lattice oxygen ascribed to the surface was modified after the doping process. In all samples, the lattice oxygen increases in the same increasing order that the stereo 3+ ions. Well, moving to the nanoparticles asphaltene interactions, it is observed that for a fixed asphaltene concentration, the observed amount increases in different orthorhombic, spherical, cubic, orthorhombic doped, spherical doped, and cubic doped nanoparticles. It has been reported that the systems with palladium and nickel improves the capability and interaction force with the asphaltenes. According to this diagram, the main mechanisms for the asphaltene uptake in the non-doped systems are hydrogen bonding and cation pi interactions. Furthermore, the non-covalent cation pi interaction occurs between the phase of an electron-rich pi system with an adjacent cation like the stereo 3+ ion. Also, the presence of nickel and palladium phases intensify the interaction with the asphaltenes, promoting diverse absorption mechanisms, including heteroatom metal interactions and pi-back interactions. Finally, according to the stereo 3 content by XPS results, these parameters follow the trend. The higher the amount of stereo 3 ions, the higher the affinity for asphaltenes due to the reduction of the phalanges absorption potential. And also, the lattice parameter and the oxygen vacancies follows a similar trend between the doped and supports materials. For the oxidation experiments, this figure shows that the asphaltenes without nanoparticles decompose entirely up to 500 degrees Celsius at 0.084 megapascals. When the pressure rises, different changes are evident in the mass change and mass change rate profiles. First, an increase in mass at low temperatures, which is attributed to the oxygen consumption in the asphaltene molecular structure, is observed. Then, there is a decline in the sample mass, mainly associated with the desorption and changes in the oxygenated structures formed. Finally, the asphaltenes finish their decomposition at lower temperatures when pressure rises. As for the isothermal analysis, it is observed that with increasing temperature and pressure, the reaction rate is improved for the asphaltene oxidation. However, a conversion of 40% of the sample is obtained in 350 minutes of heating in the best of cases. On the other hand, the catalytic effect of the material it is noted in the reduction of the composition temperature of the asphaltenes. The shape of the catalyst appears to have an important contribution to the oxidation of the asphaltenes. Minor but representative changes are observed with the different materials catalyze the reaction. The mass that the asphaltene gains vary as the shape of the catalyst changes, and it is higher for cubic systems, followed by the orthorhombic and the spherical. The Raman, the transmission electron microscopy, and the X-ray for electron spectroscopy analysis demonstrated that the cubic nanocatalyst endowed by the 111 crystal planes presents the largest amount of oxygen vacancies, which promote an effective oxygen diffusion from the gas phase or catalyst bulk phase to the surface of the asphaltenes. Therefore, this is the catalyst with more active oxygen for enhance the reactivity of the asphaltenes. Also, the main decomposition temperature peak is observed at low temperatures close to 190 degrees Celsius at 6 megapascals per cubic sample, and increases in a lower degree for the orthorhombic and the spherical. As for the catalytic isothermal analysis, it was obtained that the time required to complete the conversion increases in the order spherical, orthorhombic, and cubic. The system that required the longest time was the spherical nanoparticles, which at 0.084 megapascals and 170 degrees Celsius took 150 minutes to convert the 100 of the absorbed sample. On the other hand, the time required to convert the asphaltenes decreases with the presence of nickel and palladium phases. To explain the enhanced activity of the doped materials, two factors are considered. First, the formation and stabilization of high catalytic active sites of nickel and palladium may depend on the Surya facet's crystallographic orientation, which is improved in the cubic nanoparticles due to it is endowed by the 111 facets. The second aspect could be related to the presence of nickel and palladium lead to factor activation of Surya nanoparticles, which may facilitate the migration of the oxygen vacancies from the bulk to the surface of the Surya nanoparticles. As for the effective activation energy, it is reduced when the nanocatalyst presented a cubic shape, followed by the orthorhombic and the spherical. Besides, the presence of nickel and palladium phases reduce the activation energy values. The results also highlight the obvious effect of the exposed Surya crystal planes, the redox cycle, the content of oxygen vacancies, and the strongest interactions between the nickel and palladium species and the support on the asphaltene oxidation. Well, finally, this work demonstrated that the advantage of structured cubic, orthorhombic, and spherical Surya nanoparticles as new and promising supports with high redox properties for the asphaltene decomposition. Also, it was demonstrated that by exposing more reactive surface, crystalline phases, and Surya 3+ chemical species, it is possible to design improved Surya-based catalysts with enhanced textural and chemical properties. The data also confirms that the presence of nickel and palladium increases the catalytic activity of Surya, reducing the activation energy values in the evaluated scenarios for asphaltene decomposition at different pressures and different temperatures due to the strong metal support interactions. Finally, I'd like to acknowledge Professors Camilo Franco, Agustín Cadenas, Francisco Carrasco, and Farid Cortés, as well as the Grupos de Investigación en Fenómenos de Superficie Michael Polanyi and Materiales de Carbono for their valuable recommendations and support. Thank you so much.
Thank you very much to Universidad Nacional de Medellín, Oscar, for the great presentation. And thank you all the universities that are working today on the studies on R&D related to in situ reactions and how we can put together our different perspective on enhanced oil recovery. Here we have different institutions from all over the world. And please welcome to continue join us on these scenarios. Please remember to check the assistance list, because we are going to provide a certification of your participation here. So welcome to do it. And with that, I would like to say welcome to the next presentation. Dr. Pantano, welcome.
Our next presentation will be developed by Dr. John Pantano. John Pantano transformed reservoir numerical models into simulators for petroleum generation and multi-phase flow over geological timescales for his master and PhD. At the Atlantic Research Lab, he led the basin modeling group, and John holds 2 patents of enhanced oil recovery. He co-authored software to model spatial variability of permeability due to diagenesis, which improved Saudi Aramco pre-drill volumetric estimation. As the director of the Chevron Center of Research Excellence at Texas A&M, John guided students from engineering, geology, computer science, geochemistry, geospatial, and geophysics to develop next-generation techniques for basin modeling. For the last 5 years, his focus has been to help improve well economy by combining engineering data with rock and fluid chemistry observations and measurements in a multi-phase fluid flow framework. John has had the benefit of work with international experts across the multitude of domains to deploy these integrated solutions. We invite all the participants to write your questions or comments to Dr. John in the chat, and they will be answered in the panel section. Many thanks, Dr. John Pantano, for being with us today, and many thanks for your presentation.
Hi, I'm John Pantano. I'm so glad that the Technology Collaboration Program is doing a virtual meeting, and looking forward to the panel discussion about in situ reactions for enhanced oil recovery. Today's discussion is going to be about changing the mobility using innovative reactions that change the subsurface conditions so that we can produce more oil, keep the water in the subsurface so we don't deplete the reservoir anymore, and with these chemical reactions, energize the oil and change the oil such that it will move to the wells better. One of the key things that I've learned through my years is that the field is where you learn what really works. The field is where you understand that the subsurface is not always what we have in computer models or what we have in laboratory studies. Both laboratory studies and computer models help us optimize what sort of test are we going to perform. But in my 40 years of experience, I have found that there is something in the subsurface going on that's different than our prior assumptions. So I like to learn by doing. And in this example right here, we're bailing a well after we have actually put in some chemicals, allowed those chemicals to move away from the wellbore. Once they've moved away from the wellbore, they have actually interacted with only the formation water. The formation water itself is something that we want to keep in the subsurface. And if we can put a chemical that reacts with the formation water and somehow increases the pressures in the oil phase, and the oil phase moves, and somehow we change the mobility of the water in the subsurface, we accomplish our mission of making more oil and leaving the water in the subsurface, which gives us both pressure support and also reduces waste at the surface. So one of the places that I got a an incredible amount of experience was for ARCO, the Atlantic Richfield Company. I did a lot of work in the environmental field. I was on the American Petroleum Institute Soil and Groundwater Technical Task Force. And we did a lot of experiments in the near surface. So there's the ground surface. Different hydrocarbons were put through and spilled through the soil. And in the soil, you had clays, which are turned into shales later on, and sandstones. And then you actually have bedrock. And a lot of times this bedrock is actually an oil reservoir. And DNAPL stands for dense non-aqueous phase. So it's heavier than water and it sank. And this was light non-aqueous phase liquid, which basically would float on top of the groundwater. But above the groundwater table, we had a bunch of gas, and that's just called the capillary, the vadose zone. In the vadose zone, we did hang up a lot of oil. So the black is the oil, and we had to try to figure out how to move this oil, the non-aqueous phase liquid, out of this area. And so we tried different things, including chemical and including gas injection, which is basically we pumped atmospheric air into that and we volatilized the hydrocarbons. Well, what we learned is depending upon how you did flow rates, that dictated the amount of recovery that we could get. So by having a lot of firsthand experience and a lot of experiments, we found that we were very good near the wellbore. But as we got further and further away from the wellbore, we had an inefficient sweep or an inefficient recovery. That's where that experience said to me, how can we put something into our reservoirs away from the wellbore to create energy and change mobility? So I'm going to show you a couple of pictures of an experiment that I did in which we had porous medium at the bottom and we had oil in this porous medium. And in the test tube, we then added the water. And when we added the water, whatever oil could move would move up to the surface. So with the series of experiments, the control basically would produce this amount of oil. If you can see that boundary right there, and then this is the angle between the water phase and the side of the wall of the test tube. And so that's the control. And with the same amount of oil in this porous media, once we added the water, you can see by this volume in this area right here, we got a lot more oil out of this porous medium when we had magnesium metal out into the porous media. So to make you look a little closer, we start off with oil and gravel. Then we drain, so that those are little pieces of grains of rock. And we then dump out all the oil, and then we add this colored water is red. And after we've added that water and we've had the chemical reactions in the porous media, we get all this oil out of the system. And now we're going to zoom in. And basically, these little particles down here that you probably can't see very well, they were about 100 microns. And it was very easy for those small particles to be dropped into the water oil system. They fell down and they reached all the way down. So having small particles allows the small particles to get out into the system. Now right here, when it's in the system, it went in as the oil phase, and it really didn't start to chemically react with the formation water. This is after about 2 days, it started to react. And this reaction was an alkaline metal with water, produced hydrogen gas. It created heat, and it also created hydroxide. And hydroxide is when you think of an alkali surfactant flood, that is an alkali. So that hydroxide changes the wettability of the oil, and that gas actually helps change the mobility and has forces to create. And so you start off with this big oil bubble, and later in time, that oil bubble goes through smaller and smaller and smaller. So this residual oil has basically, after the reagent is used up, in this case here, all the oil has been moved. So how does this work and where does it work? Let's look at a reservoir. And so the best part of the reservoir that we would have, and these would be grains of rock, and the black is our oil. And at the time, if we could get those particles of that reagent, so the chemical that won't react with oil but will react with water, at this time it would not react. As we produce, we're going to get to what they call the residual hydrocarbon saturation. At that point, we have a lot of water, and that's where we want our chemical reactions to occur. And when those chemical reactions occur, we should be able to mobilize more and more of this material. Now, the good thing about this is that we can put this stuff, because it's in small particles, we can go down to nanoparticles. And I found that the nanoparticles, I stopped doing experiments with things that were nano size, because the surface area was so great, the reaction rates were much, much quicker. And I think that's very good in the subsurface. I did have a laboratory that was capable to deal with that type of reactivity. And that's a major thing to consider. We need to make this economical. So if you make an exotic nanoparticle, that might has to be balanced in terms of how much oil recovery can you get compared to commodity materials. And the commodity materials are usually cheaper, and they're going to be less reactive, but it might just be a cost benefit analysis for you to figure out with your reservoir what is the right balance between cost of your reagent, the way that you distribute the reagent, and then the amount of oil that's recovered. So thank you very much for your time, and I look forward to the panel discussion. Are there any questions?
Thank you, Dr. John Pantano. Wonderful presentation. And thank you all of you for being here connected today. I have been seeing into the chat. Thank you, Dr. Berna, for answering the questions that come in as well into the chat. And as well, question for Dr. Pantano. Dr. Pantano, John Pantano is here today as well with us. Please feel free to ask the questions, and as well coming into our panel discussion after this series of presentations. We will continue on. So let's bring now our next presentation. Thank you.
Our next presentation will be developed by Alain Novaes. She is a chemical engineer with a master's degree from Universidad Federal do Rio de Janeiro. She has been working in Petrobras since 2011, mainly in rock fluid interactions in Petrobras Research Center. Alain worked with Rafaela, also a chemical engineer with master's degree from Universidad Federal do Rio de Janeiro, who has been working in Petrobras since 2009, also in rock fluid interactions in Petrobras Research Center. They will present to us rock fluid interaction during WAC injection experimental development and reactive transport simulations, and will tell us about calcite and dolomite dissolution due to the presence of CO2 and disulfated water that enable series of chemical reactions affected by temperature, pressure, mineralogy, fluid composition in the reservoir. We invite all of the participants to write your questions and comments for Alain in the chat, and they will be answered in the panel session. Many thanks, Alain, for being with us today and for your presentation. Thank you very much.
First of all, let's establish the scenario found in pre-salt reservoir. As we all know, water injection is the most used method for secondary oil recovery. In our projects, the sulfated seawater is usually chosen to avoid problems with scaling and souring. Due to the presence of high amounts of CO2, WAG injection became a very good option. It's a way to deal with all the CO2 that's going to be produced and also to enhance oil recovery. Pre-salt reservoirs are formed basically of carbonate rocks that are reactive to injected fluids. The reactivity is increased by the presence of CO2 and can be affected by temperature and pressure. Reactivity causes changes in the composition and pH of produced water. It can also affect porosity and permeability, especially in the injection zone. Kinetic and thermodynamic parameters for the reactions are hard to obtain and are normally available in surface conditions. Experimental work was also developed to determine the parameters in reservoir conditions. Now, let's talk about reactive transport. The definition is pretty simple. It's the transport of a species in the porous media. But what does that mean? Well, let's take this simple example. When we don't have reactions in the reservoir, the produced water is going to be a mixture between injected water and formation water that is present originally in the reservoir. But when we have reactions taking place, which is the case for carbonates, this is no longer true, at least not for all the species. For some species, the produced water is going to be a combination of injected and formation water, but it's also going to have these reaction products. So this needs to be taken into account in order to have a good prediction for produced water composition. Just to summarize, in case of the carbonates that are reactive under fluid injection, water interacts with the reservoir rock, changing produced water composition. The inclusion of those chemical reactions is mandatory for carbonates. This kind of modeling is called reactive transport in porous media, and it's what we do every time we need to establish the composition of produced fluid when dealing with WAG injection in pre-salt conditions. To illustrate what I just said, let's take a look in the injection of the sulfated seawater in a carbonate reservoir. First of all, we have the dissolution of the CO2 in the water. The CO2 can come from the oil or from the reinjected gas in the case of WAG. So the CO2 is going to pass to the water and is going to cause a decrease on the pH due to the release of the H+ ions. If we stop right here, we're going to have a low pH in the produced water. But it's not what happens when we are dealing with carbonates. In this example, the reservoir is made of calcite and dolomite. So the H+ that is released by the passage of the CO2 for the water is going to attack the rock, causing its dissolution. Here, for calcite dissolution, the reaction number 1, we have the H+ attacking the calcium carbonate and releasing calcium and bicarbonate. So the amounts of those ions, calcium and bicarbonate, is going to be higher in the produced water, as well as the pH when compared to a scenario where we don't have any kind of reaction. The same thing is true for dolomite, but in this case we have this mixed carbonate of calcium and magnesium. So we have the release of calcium, magnesium, and bicarbonate, increasing the concentrations of those species in the produced water and also the pH. As mentioned before, experimental work was done to obtain the parameter for the reactions. On the left, we have a schematic of the reactor that we used. It was a PAR reactor made in alloy to be able to deal with big amounts of CO2. So in this reactor, we can put rock, fluid, and also gas, and sample the water to obtain the growth and the changes in the composition through time. On the right, we have a representation of a test result. In this case, the rock was pure calcite. We worked in a pressure of 4,000 psi and 60 degrees Celsius of temperature, and also in the presence of CO2. As we can see, only the pink dots show changes in the composition. The pink dots represent the concentrations of calcium through time. The growth means that calcite is being dissolved until a plateau where the reaction reaches equilibrium. All the other species that were analyzed, magnesium, sodium, and chloride, show no changes in concentration through time, meaning that they don't take part in any reaction. Only calcium is changing, and also bicarbonate that is not being shown in this graph. Besides laboratory experiments, we were able to run a field test to show the effects of rock-fluid interactions. So we had a backflow test in a well. We injected a volume of water, closed the well for a while for a soaking period, and produced the water again. The graphs show the variation of concentration for calcium and bicarbonate in milligrams per liter through time. On the left, we have the result for calcium, on the right, the result for bicarbonates. The blue line represents a non-react case, which means that is the values we would expect for those ions if no reaction was happening in the reservoir. The red dots represent field data, which means that those values were measured during the test. We can see that's a huge difference between the field data and the no-react case, showing that calcite dissolution was real under reservoir conditions. To estimate the pH of a fluid in contact with rock in the presence of CO2, we used a geochemical software called ArcSym. To check if the values that were being estimated by the software were okay with the reality, we have a special reactor with a pH electrode inside. That means we can measure the pH inside the reactor in reservoir conditions. So the results of the tests are shown in this table. The first test was only water and CO2. It's a salinity of 30,000 ppm, that's compatible with the sulfated seawater, saturated in CO2. In this case, we don't have any rock, so we only have the CO2 in the water. The measured pH was 3.07 and the estimated pH 3.12. The second test was the same water, but instead of CO2, N2. The pH was much higher, 6.1 the measured pH and 6.17 the estimated pH. And the last one is the most interesting test, the same water saturated with CO2, but in the presence of calcite. In this case, we expect calcite dissolution to increase pH, which really happens. The measured value for pH was 4.53 and the estimated value for pH 4.51, showing that the predictions of the software are very good fit with the measured values. To see the changes in permeability, we have reactive flow tests. In those tests, we can inject a water with or without CO2, and we can analyze the composition in the outlet of the plug. This is an schematic of the plug flow test, and here is a picture of the equipment. On the left, we can see the variation in the composition for calcium, magnesium, and bicarbonate. In this particular case, we had mainly dissolution of calcite, shown by the values of calcium bicarbonate that are pretty high and the low amount of magnesium compatible with the sulfated seawater. On the right, we have the variation for mass and permeability. For the mass, we can estimate the variation by the changes in the composition. For permeability, we can estimate the permeability by measuring the pressure and the flow rates. We can see here at the end that we have a big growth in permeability, and at a point we weren't able to measure anymore. It means that we have a wormhole connecting the inlet and the outlet of the plug, so we can no longer measure the pressure, and permeability goes to infinity values around 64 volumes injected. Until now, we have been discussing the injection of the sulfated seawater, but now we're going to see what happens when we work with seawater. So the main difference from seawater to the sulfated seawater is the sulfate amount. It goes from 2,800 in the seawater to less than 100 in the sulfated seawater. But we also have a big change in magnesium. It goes from 1,400 milligrams per liter in seawater to values that can go as low as 80 milligrams per liter in the sulfated seawater. So the difference in the amount of these two components cause two different reactions that we can see only in seawater and especially in high temperature reservoir. The first one is dolomitization, represented here by reaction number 2. Is the conversion of calcite in dolomite. It consumes magnesium and releases calcium in the water. And the second one, represented here by reaction number 3, is anhydride precipitation. It consumes calcium and sulfate and forms anhydride in the reservoir. Reaction number 1 is calcite dissolution that happens also with the sulfated seawater and seawater. When we first started studying the injection of seawater, we had a doubt regarding dolomite. We saw in the reactor tests that magnesium was being consumed, but we didn't know exactly if the reaction taking place was dolomitization or just the precipitation of dolomite. And what is the difference? Dolomitization is represented on the left. It happens with consumption of magnesium and release of calcium, as we can see by the equation. On the other hand, dolomite precipitation happens as the equation on the right, and it consumes calcium as well. So when we are dealing with seawater, it's very important to guarantee that the sulfate that is being injected is going to be trapped in the reservoir on the form of anhydride. And we can see by those mechanisms for dolomite that we can have a big difference depending on the mechanism that we take into account. If we look to the left for dolomitization, calcium is being released. It's as a communal effect, it's going to help anhydride precipitation because we're going to have more calcium to be precipitated alongside with sulfate. If we look to the right on dolomite precipitation, calcium is always being consumed. So they are going to compete for the same calcium, both dolomite precipitation and anhydride precipitation. And as we favor one, we are going to stop or make the other one weaker. So it was very important to find out which mechanism was going to take place under reservoir conditions. Dolomitization by releasing calcium and helping anhydride precipitation, or dolomite precipitation that is going to consume calcium and makes the anhydride precipitation harder. So we held a series of reactor tests, putting sulfate and magnesium and removing one of them. And we came to the conclusion that when we have magnesium in the water, the mass of anhydride precipitation was 2.95 grams. When we didn't have magnesium but kept the same conditions, the exactly same conditions, we had a precipitated mass of 2.05 grams. As we can see, with magnesium in the water, we had higher precipitation of anhydride. As we had exactly the same conditions, we can say that the mechanisms that was acting there, it was dolomitization. And that's why it was helping anhydride precipitation, and that's why we have a higher mass of anhydride when we have magnesium in the water. So the conclusion of those tests was the presence of magnesium increases precipitation. Therefore, we can take dolomitization into account and not the precipitation of dolomite. To validate the models for seawater injection, we have some field data for 2 wells in a reservoir where seawater has been injected. This is a high temperature reservoir, so the results are very good. Here we have the sulfate and magnesium in milligram per liter as a function of injected water in the produced water. We can see in both graphs that we have a dark red curve representing a non-reactive scenario. That means that in this case, the produced water is merely a function of the mixture between injected water and the formation water. For sulfate and magnesium, we can see a growth in the concentration due to the high values of sulfate and magnesium in the seawater. The blue circles represent the result of the reactive model. So for the reactive model, we have both reactions happening. The dolomitization that is consuming magnesium and the precipitation of anhydrite that is consuming anhydrite. The red triangles and the green square represent real data. So those are results that were measured on the field for two different wells. We can see that for both sulfate and magnesium, field data is much closer to the reactive model, showing that consumption of sulfate happened due to anhydrite precipitation, as well as consumption of magnesium due to dolomitization. These results can prove the modeling that we have been using for seawater injection. To represent the importance of rock-fluid interactions, we have here a little schematic to show where we work and what our results can help to predict. So we have both experimental and simulation works, and everything is connected. Everything that goes to the simulator, the parameters, and the reactions, all the understanding that we have and we put in the simulations comes from experimental results. And when we run a simulation, we can be looking for two main things: composition and pH of produced water and change in porosity and permeability near well. For composition and pH of produced water, the results can be applied to material selection because the pH, we have talked about that and we have seen that the pH in the produced water is bigger when you have chemical reactions happening in the reservoir. So we can be using materials that are less expensive than we would have to if we didn't have any reaction going on. And mainly that produced water composition are for scale and prediction. So as we said before, those reactions change the composition of produced fluid and they have to be taken into account in order to have good scaling predictions. And also to evaluate if we can bypass the SRU, so if we can inject seawater alongside with the sulfated seawater, or if we can inject only seawater, and studies like that. And regarding the change in porosity and permeability, those studies can help a geomechanic. We can see if the changes caused by reactivity can cause changes regarding mechanical properties of the rock, and also for injectivity. That's a very important parameter because we always need to inject water in the reservoir, and some reactions can help the injectivity and can allow a higher injection of water in the reservoir. And we are also working a lot now with history matching in terms of composition. So we get the data from the field, the composition data from the field, and then we go back to the models to see if the results that we are generating in the models, if they are correct, and try to find out what's going on if they aren't. For example, if we're making a mistake in the assumption of mineralogy or something like that. And then we have to produce better models in order to have a good matching, and therefore, in the end, we have more reliable reactive transport simulations. Now we're going to see some simulation results for a WAGI injection. On the left, we have a picture of the injector well for a case of 80% of CO2 in the injected gas. The property is diporo, that is the final porosity minus the initial porosity. We have porosity changes due to dissolution of calcite. So in the injection zone, the porosity is expected to increase, as we can see by the colors in the blocks that are signalized by the arrows on the left picture. On the right, we have a graph for block 13, that is the one that has shown the biggest variation in the porosity. On the graph, we see the variation of calcite fraction through time. We have four different scenarios: a non-reactive case for 80% of CO2 in the gas. In this case, there is no reaction taking place in the reservoir. That means that we don't have calcite dissolution, and therefore the calcine fraction is the same all the time. For the other three scenarios, we have calcite dissolution, but we have the effect of the amount of CO2 in the injected gas. The higher the value of CO2 in the gas, the more reactive the system gets. So the variation for calcite fraction is bigger for the case where we have the higher value of CO2, that is 80%. The smaller variation is observed for the case where you have 20% of CO2 in the injected gas. The 50% gets in the middle. So we can see that the light blue curve is higher in terms of calcite fraction than the green one that is higher than the red one, which means the red one is the most reactive case due to the amount of CO2 in the injected gas. On the previous slide, we saw the changes in porosity and calcite fraction for the WAG injection. Those changes are expected in the injection zone. Now we are going to analyze the changes in the produced fluid. On the left, we have the changes in calcium concentration through time. On the right, we have the pH changes through time. All the scenarios are the same as before. Non-reactive for 80% of CO2 on the gas, reactive for 80% of CO2, 50% of CO2, and 20% of CO2. As said before, the most reactive case is obtained for 80% of CO2 in the injected gas. Therefore, the concentration of calcium is expected to be higher in the produced water for this particular scenario, is what we can see by the red curve on the left graph. For the 50% of CO2, we have the green curve, and for 20% of CO2, the light blue curve that are a little smaller than the red one. The smallest values of calcium are obtained for the non-reactive scenario, where we only have the mixture between injected water and formation water. For pH, the smallest values are also obtained for the non-reactive scenario. We have the mixture of the fluids and also the passage of the CO2 to the water and no consumption of the H+. So we have very low values of pH that can reach 3. For the reactive scenarios, we have a difference when compared to the calcium concentrations. For the pH, the biggest values are observed for the case with 20% of CO2 in the injected water. It means that we have a competition between reactivity and the lowering of pH due to the CO2 passage. So we have higher pH for smaller amounts of CO2 and smaller pH for higher amounts of CO2. And that's why we have smaller values of pH in the red curve. To finalize the presentation, some conclusions about what has been said. In carbonates, the injection of water can cause chemical reactions that will affect the composition of produced fluid. Those reactions can be even stronger in the presence of CO2. Although the CO2 can lower the pH of the produced water, the reactions are going to increase the amount of bicarbonate and consume the H+, so we have much higher pH in a reactive scenario. Laboratory tests and field data confirm the extension of reaction under reservoir conditions. Desulfated seawater and seawater can affect the system in different ways depending on temperature, pressure, and CO2 amount. As we saw, when we have seawater and high temperature, we can have two reactions that don't happen with desulfated seawater: dolomitization and anhydride precipitation. In order to have good predictions for produced water composition and pH, reactive transport models are mandatory. So every analysis that we need to do for carbonates have to take into account the reactivity of the reservoir and the changes that it's going to cause in the produced water composition.
Thank you, Dr. Alisa. Really appreciate all your comments and your questions into the chat. And thank you to all of you. Please, we would like to welcome you. Let's take a group photo before our next speaker. I really appreciate it. You can put your cameras on. So like this, we can get a quorum into the camera. Really appreciate it. So happy to have all of you here today. We have continents from all over the world here connected, connected from Asia. We have connected from Africa. We have connected from Europe, from Americas, from Caribbean regions. Thank you, all of you. Let's get and take a group photo. Thank you for have you all here and this mercy journey. Thank you for your comments as well into the chat, and please fulfill the form. Let's take a photo. Just give you coming on. Oh, Dr. John Patano, where are you? Are you like in Egypt? The background? Hi, Oscar. Great to see you. Hi, Hernando. Yesenia. We're all connected from China now. Yeah. Thank you, Dr. Khaled, for an amazing job. Thank you, Dr. Berna. Great to have you all of you here.
Gracias, César.
Okay, Ciro. Thank you. Hi, Daniela. Great. Okay, let's take a group photo now. We have all the camera on now. At least you help me with that, Adriana. Okay, cool.
Yes, please. 1, 2,
Excellent.
3.
Just say EOR, EOR.
EOR.
EOR. Thank you. I really appreciate your support.
The second screen.
Okay, okay. Okay, the second picture.
Thank you.
Thank you. Thank you very much.
Thank you. Hello, Dr. Guo.
Thank you, William.
Thank you. I am
Okay,
happy to
let's go.
see my old friend, Dr. Guo Erden from China. We used to him before. He's in one project.
Yes, it's great to see our family, our EOR families here all around the globe. And that's a good thing. Hopefully, this year we're supposed to be in Australia, to be connected. And next year is going to be in Russia, in St. Petersburg. So hopefully we can meet in Russia in the EOR TCP workshop worldwide. So let's be ready for that. After Australia meeting, we are doing virtually this year. Hopefully next year we can meet in St. Petersburg in Russia. So with that, let's go continue on it, and let's go for our next presentation. Thank you. And then we panel discussions. Please put your questions in the chat. Thank you.
Thank you. Let's continue.
Good morning, everyone. Our next presentation will be developed by Oscar Medina. Oscar is a petroleum engineer with an honorary degree from the National University of Colombia. Doctoral student in engineering, energy system and same university, and doctoral student in chemistry and the University of Granada, Spanish. Research and has more than 4 years of experience in nanotechnology applied to the oil and gas industry, synthesis and characterization of nanomaterials, EOR and EOR process. Author for more than 20 scientific articles published, a patent, a book chapter, and other international events. Many thanks, Oscar Medina, from begin with the use today from your presentation. Thank you.
Hi, good day everyone. At this time, I have the honor to present the most recent advances of my doctoral thesis focused on the kinetic oxidation size of the heavy crude oil at high pressure, high temperature conditions based on asphaltene-asphaltene interactions. This work has been developed in the Universidad Nacional de Colombia in the research group Fenómenos de Superficie Michael Boulangi, with the contribution of the Universidad de Granada and the University of Calgary. The agenda present today consists of a brief introduction, the main objective of this work, the methodology used, the most relevant results and conclusions, the bibliography used to construct this presentation, and the respective acknowledgements. The composition of the crude oil is complicated, so it is conventionally divided into saturates, aromatics, resins, and asphaltenes. In the specific case of the heavy and extra heavy oil, asphaltenes are found in mass fractions between 3 and 30%. These compounds are the heaviest and most polar fraction of the crude oil matrix, and the location and high content of heteroatoms in the molecular structure lead to high polarity, which provides their set of assembly characteristics, generating a rigid and stable viscoelastic network that prevents the crude oil flow and making necessary the addition of energy by means of heat to improve the production operations. During in-situ combustion, the heat is propagated throughout the reservoir by igniting heavy and extra heavy oil, injecting air or oxygen-enriched gas into the formation, and subsequently reducing the onboard oil viscosity and improving its flow. However, the in-situ combustion faces several challenges pertaining to the combustion front instability and the increase in the oil viscosity due to the low temperature reactions. Also, the heaviest fraction are transformed into coke at low temperatures, and a greater number of oxygen-containing compounds are produced. So, to achieve an optimum petroleum operation design, it is important to understand the chemical reaction and thermal behavior of asphaltenes, since they are known as co-precursors during the low temperature reaction. In this sense, it's really important to understand and study the development of the addition reactions during the oxidation processes, which also depends on the asphaltene chemical nature and the asphaltene aggregation phenomenon. So, this work is interested in the study of the thermo-oxidative decomposition of heavy oil based on the understanding of the oxidative behavior of asphaltene model molecules in aggregates. The proposed methodology to fulfill the mentioned objective consists first in the characterization and construction of asphaltene molecules. For this, asphaltene isolation was done from 7 different heavy and extra heavy crude oil samples obtained from industrial partners around the world. Then, the asphaltenes were characterized in terms of elemental analysis to determine the elemental composition of carbon, hydrogen, sulfur, nitrogen, and oxygen, vapor pressure osmometry to calculate the molecular weight of the sample, nuclear magnetic resonance to obtain information about the hydrogen and carbon distribution on the asphaltene molecular structure, X-ray diffraction to obtain information about the structural parameters of the molecules, and the X-ray for electron spectroscopy to determine the carbon, nitrogen, sulfur, and oxygen species in the molecules evaluated. Then, based on density functional theory calculations, the molecules were constructed and fully optimized using the biggest 3-parameter and leading part functions. Also, the Clark's theory of the aromatic system was used to predict the stability of the aromatic systems. As for the asphaltene aggregates,
Different model solutions were prepared by slowly adding a determined amount of asphaltenes to form aromatic solvents, while the mixtures were magnetically stirred at 300 revolutions per minute during 30 minutes. The asphaltene aggregate size on the different solvents were registered by a small angle X-ray scattering, and the viscosity was determined by rheological measurements. As for the oxidative experiments, a high-pressure thermogrammetric analyzer was used. These experiments were developed in three main subsections that involve asphaltene oxidation for a single source in a wide range of pressure between 0.084 and 7 megapascals. The second subsection includes the oxidation of different sources of asphaltenes at low and high pressures. Then, two representative molecules were selected for analyzing these interactions with oxygen at high pressure using dynamic molecular simulation through the reacts if potential. This potential employs a bond order formalisms in conjunction with polarizable Krag descriptions to describe both the reactive and non-reactive interactions between the atoms. Finally, the third topic consists in the oxidation of asphaltene model solution at high pressure to obtain information about the aggregate state influence on its reactivity. In this section, it was evaluated the effect of the asphaltene mass in the effect of methyl addition and position in the reference solvent. Asphaltene molecules were experimentally resolved. The results suggest that a structural difference exists between each molecule, checking the parameters obtained experimentally in the different characterization techniques. Some of these properties were found similar for asphaltenes 1A, A, B, and C. These asphaltenes present a higher hydrogen-carbon ratio, a higher content of aromatic carbons, higher degree of aromaticity, higher distance between neighboring aromatic sheets, higher degree of condensation, and higher content of thiophene, pyridinics, and carboxyl groups. Well, the first question that arises to fulfill the main objective of this work is, what is the effect of pressure on the asphaltene oxidation? This figure shows the mass change and temperature profile as a function of the time for the asphaltene oxidation at 6 megapascals. According to the mass change profile, the temperature was divided into four defined regions. The first one is named as oxygen chemisupption region and corresponds to the interval where an increase in the asphaltene mass is observed, associated with incorporation of oxygen atoms on the asphaltene molecular structure from the oxygen-rich environment. The second region, known as the decomposition of chemisorbed oxygen region, is the temperature interval where the first decomposition and desorbed of oxygenating compounds occurs, that is, where the mass sample begins its reduction. Then, for higher temperatures, the combustion phenomenon is divided in two main regions, first and second combustions. These intervals were separated according to the thermal event close to 400 degrees Celsius clearly observed in the temperature profile. The total consumption of the asphaltene is carried out at the end of the second combustion, and each region is defined by a particular behavior associated with its mass change and mass change rate curves at the time of its decomposition in mathematical functions, conventionally Gaussians and Lorentzians, which perfectly describe the area under the curve. Thus, the effect of pressure was evaluated on the 1A asphaltene oxidation. According to the results, asphaltene oxidation is a pressure-dependent phenomenon due to both profiles. The mass change and rate for mass change are modified with increasing pressure. For atmospheric pressure, the asphaltene profile is divided into low and high temperature regions, and the OC and DCO do not occur for pressure lower than 0.7 megapascals. Also, it is noted that pressure generates a positive effect on asphaltene oxidation, reflected in the number of intensity peaks at the rate for mass change, favoring the asphaltene consumption at lower temperatures as a result of the oxygen chemisupption region. Considering these results, it is important to understand what is the effect of the asphaltene chemical nature on its reactivity at different pressures. Here are shown the thermograms obtained at the three pressures evaluated for each asphaltene. For all cases, the asphaltene thermo-oxidative decomposition profile is determined by the four mentioned events. However, some differences were found. The first one is related to the oxygen chemisorption percentage, which was higher for the A, B, and C asphaltenes. In agreement, it was found that some properties follow a direct relationship with this variable, including the oxygen-carbon ratio, which increases the oxygen chemisorption percentage. Also, the presence of carboxyl groups favors the oxygen chemisorption because this species can be ionized by releasing a proton, that is a nitrogen atom from a nitroxyl group, and respond to carbon interactions with carboxyl group and neighboring carbon. Another important result was found related to the content of beta hydrogen on the alkyl chain linked to the aromatic ring and the aromaticity factor. As the aromatization degree increases and the alkylation degree decreases, the chemisorbed oxygen atoms also increase. Similarly, the mass loss in the DCO region was favored by the same asphaltenes, according to the high content of short aliphatic chains and the heteroatoms located in ramification of the molecular structure. Other important fact is that the D, E, and F asphaltenes exhibit a considerable increase in the intensity of the peak at 6 MPa during the fast combustion, related to the increase in the collision probability between the oxygen molecules, thus higher kinetic energy triggering rapid exothermic reactions with the aliphatic chains, promoting the asphaltene dealkylations. These results are corroborated with the amount of mass lost for the systems during the FC region, where a triple of mass loss was observed for the D, E, and F asphaltenes compared to the A, B, and C samples. In addition, the mass loss is correlated with the high aromatic character of the asphaltenes D, E, and F, and its values for the total aromatic rings and thiophene and pyridinic content, which increases the condensation degree of the samples and improves its decomposition at higher temperatures. Well, based on these results, the B asphaltene was selected to evaluate its interactions with the oxygen molecules at 6 MPa using molecular dynamic simulation. First, it was obtained that the oxygen molecule attacks the aromatic ring alpha and breaks its conjugation. Then, the 6-member ring beta degenerates into 5-member ring gamma, and the hydrogen atom on the phenolic group is transferred to the aldehyde carbon to form an aldehyde group. At the same time, the sulfur is oxidized. Finally, the oxidation of sulfur is completed, and at the same time occurs the oxidation of the pyridinic group. As for the second family, the E asphaltene was selected to evaluate its interaction with the oxygen, and it was found that first, the oxygen molecules tend to attack also the aromatic ring alpha and breaks its conjugation, forming two ketone groups. Then the oxidation of another aromatic ring occurs and the oxidation of sulfur takes place. Finally, the oxidation of the other heteroatom on the asphaltene molecular structure occurs, and all these results imply that regardless of the asphaltene chemical nature, at high pressure conditions, the oxygen tends to attack first the aromatic core, and then the heteroatoms located on the aromatic structure. Finally, the third question to resolve is how asphaltene aggregates behave under oxidative atmosphere at different pressures. Here are shown the results from Sachs and experimental relative viscosity for the different asphaltene concentrations dissolved in toluene, P, M, and O-xylene. Clearly, the length of the asphaltene aggregate is correlated with the viscosity values of the solution models. The viscosity increases as the size of the asphaltene aggregate increases, and in turn the viscosity increases as the asphaltene concentration in the model solution increases. For both low and high asphaltene concentration, the viscosity increases in the order toluene, O-xylene, M-xylene, and P-xylene, indicating that the addition of a methyl group in toluene molecules changes the asphaltene-asphaltene interactions. Up to this point, it is believed that the aggregation mechanisms at high concentrations occurs mainly through pi-pi stacking interactions between the aromatic cores. As for the oxidation, the effect of the asphaltene content was assessed using toluene as reference solvent. As a first instance, it is observed that regardless of the asphaltene concentration, the thermograms are described by the four thermal events. Interestingly, substantial differences were found in the different stages as the asphaltene content increased in the model solutions. The thermograms shows that the amount of oxygen conserved increases as the asphaltene concentration decreases, which is intrinsically attributed to the size and surface area of the aggregates and the subsequent thermal expansion. The results suggest that the smaller aggregates present a higher surface area volume ratio, and therefore they present a higher number of active sites for interacting with oxygen. For example, aromatic structures are less exposed to the oxidation, like pyridines and thiophene, which play a fundamental role in the oxygen chemisorption, will not be clogged in the aggregate complexes. In addition, the intensity of the two last peaks in the first and second combustion increases with increasing asphaltene aggregate size. This is a consequence of the low reactivity that samples present due to the low oxygen chemisorption and the more condensed structure resulting after the desorption of chemisorbed oxygen region. As for the effect of methyl addition in position, it is noted that the mass gain in the oxygen chemisorption for the three systems with one more methyl is less than for the toluene, while among them this variable increases in the order O-silane, M-silane, and P-silane. In this sense, depending on the solvent used, asphaltenes have greater or lesser interactions between them and the solvent. This result also confirms that asphaltenes are capable of interacting with neighboring asphaltene molecules through several intermolecular forces, including London dispersion forces between aliphatic moieties, pi stacking of aromatic cores, hydrogen bonding between nitrogen and oxygen-containing functionalities, and acid-base interactions. Also, as a consequence of the mass gain in the oxygen chemisorption, the rest of the thermal events change to a greater extent. First, the TCO region for P-silane ends first at the in M and O-silane due to the few oxygenated structures formed. Afterwards, both the first and second combustions end at higher temperatures, and the main change is observed for the second combustion region, where the profiles for the model solution of asphaltenes with M and O-silanes present a small peak between 400 and 500 degrees Celsius, which in P-silane this is the predominant peak of the curve. Well, among the main conclusions of this work are the importance of the addition reactions at high pressure conditions. It has been observed that depending on the chemical structure that the asphaltene acquires in the oxygen chemisorption region, its reactivity changes in the rest of the thermal events. On the other hand, the interactions between the oxygen and asphaltenes depend on their chemical nature. So it is important to know the composition of the crude oil in the field in which an Insitu combustion process will be carried out and determine the operating conditions to avoid the exothermic and violent reactions at higher temperatures. Then, the interactions between these molecules gains importance at high pressure, since depending on the size of the asphaltene aggregates, the reactivity of the molecules decreases. Furthermore, it was determined that during the oxidation of the asphaltenes, other intermolecular interactions gain priority thanks to the oxidation of their molecular structure. All these findings suggest that the asphaltene oxidation is controlled by the sequential reaction mechanisms which change under high pressure conditions. It is essential to consider all these analyses to understand the thermal mechanisms that can affect the in-situ combustion processes and thus be able to develop the technology with more cost-effective benefits. Finally, this is the bibliography employed to construct this presentation. And I'd like to thank the professors Camilo Andrés Franco, Farid Cortés, Jaime Gallego, and Nassar Nassat, as well as the group of the Investigación en Fenómenos de Superficie, Michael Polanyi, for their valuable recommendations and support. Thank you so much.
Thank you all our panelists, Oscar. Thank you. Please welcome to open your cams, your cameras, and we can continue now with the set of questions. Thank you all for being here today. Thank you, Dr. John Pantano. Thank you, Bernard. Thank you, Oscar. Thank you for being here today. Thank you for having answered already the question. Thank you, Aline, as well for your great presentation with the result and how we can put these lessons as well. Thank you for everything together put it here. Comment related to CO2 sequestrations and how the enhanced oil recovery processes can be connected. We have been seeing a lot of window and a lot of lessons that we can put together. As part of the enhanced oil recovery technology collaboration program, that is something that we are working now to articulate with the International Energy Agency related to decarbonize our assets and our projects. And that would be a question to all of you. How do you think we can extrapolate these in situ reactions into the different CO2 conditions, as we have been seeing with Berna, on the conditions we have it, as we see with Dr. Hali, with John and Aline on pre-salt. Is an alternative to apply and go further to mature assets. That is going to be our challenges. How do you think will be the best way, and will be the questions for all the panelists, to pull all these aggregation integration on CO2 reactions to decarbonize, like part of the in-situ reaction processes? So let's start with Berna. Thank you.
Okay, so Cesar, it's a good question, very good question. For carbon dioxide sequestration perspective, I'm also teaching carbon dioxide sequestration, and I just wrap up with my summer class carbon dioxide, and we reviewed a lot of carbon dioxide sequestration projects all around the world in that class. And some of the carbon dioxide sequestration is targeting actually enhanced oil recovery, but instead of producing carbon dioxide, leaving the carbon dioxide in the reservoir forever. And there are some successful studies like that. Nearby the Canadian border, we have here in the United States a carbon dioxide sequestration project still going on as an enhanced oil recovery, but since we are not producing carbon dioxide, just producing oil and leaving behind the carbon dioxide by just getting benefit of some of the reactions that they have been told. Also, we reviewed between the water and the carbon dioxide in the our aim in carbon dioxide sequestration is just trapping carbon dioxide in the mineral form, calcium carbonate. And we reviewed some of those reactions in a reverse way, and we obtained bicarbonate in one of the presentations. So our aim is here, making carbon dioxide trapped in the mineral form, and it is achievable even for enhanced oil recovery. But this is not a kind of a short-term goal, it's a long-term goal, which means that after you sequester the carbon, you need to monitor it, how the sequestration is going. And the mineralization is not then a quick process. It will take 1,000 years. So our lifetime will not be sufficient enough to capture it. But if we can trap the carbon dioxide properly in the water and in the pore space, then it is achievable as long as we know the physics and as long as we know the background knowledge. So I hope it is answering your question.
Thank you, Berna. Yes, and the same question to Aline. As pre-salt has a great challenge as well, there are some assets, some reservoir that has CO2 on the production as well. How we utilize this as part of the reactions that you have been seeing? Something to add, Aline? Thank you.
Yeah, thank you. Well, for pre-salt, as the presentation, we are looking for CO2 more as an enhanced method to have more recovery of oil, and also to have a way to deal with all the CO2. It's not exactly produced, but it's not retained in the reservoir. But yeah, just we have the same point of view that was explained before, to retain the CO2 in the reservoir, to go for reactions that are exactly the opposite of what I've shown. So I'm talking about dissolution of calcite And so to sequestrate the CO2, we need to go for the precipitation of carbonate. So depending on the conditions of reservoir, it's not exactly the pre-salt reservoirs are not good for sequestration, but if we have different conditions, we can go for precipitation of carbonates and to retain the CO2 in this mineral form. So it's similar studies, but different results at the end.
Okay, Alice. So, and you can put like a natural cycle, yes? We have in nature, how retention, how emissions as well related to the pre-salt ecosystem, let's say, about the CO2 cycle.
Yes, yes.
Okay, and I think that that is something that we should keep an eye, how our EOR technology, how our EOR studies can articulate it on this CO2 sequestration, but as well on the productivity with enhanced oil recovery processes that will aggregate on these different changes we are doing in the reactions to surface and surface to put the best value. Thank you, Aline. Yes, John, and any feedback about it?
Yeah, you know, one of the things that I looked at, you know, half my career is environmental, half my career has been oil and gas, and studying the carbon cycle. We always want to utilize things as much as we can, and we would like things to be a source as opposed to a sink. So we want to actually see if we can get more of that inorganic carbon that we create at the surface to be in the subsurface. So one of the solutions that I've come up with is to use CO2 as the carrier fluid for the reactive material. And when you carry that reactive material into the subsurface, and then that subsurface formation water reacts with the reactive material, it actually will produce a hydroxide. And that hydroxide actually then offsets the carboxyl acid or the phases of CO2 in the subsurface. So you can basically try to mix together a reactive material that's compatible with the formation for water and the oil, the hydrocarbon phase, and such that you can start to do blocking of those water channels in the subsurface. So it's one of these creative things where we don't just want to sequester, we want to utilize all that CO2. So the more we can recycle things, that's what I'm always advocating for, and not pure sequestration.
Thank you, Dr. Pantano. I really appreciate your feedback. I completely agree with you. Dr. Khalid, anything to add? Your mic is off.
Yes. Can you hear me now? Yes.
Yes. Thank
you. Yes. I agree with Dr. Pantano that I'd like to see the carbon more out than in, so we live in a carbon economy, so we cannot have enough of the carbon. However, maybe we need to look at the things a little bit differently. I mean, that's always my approach in life. It's always unconventional. I'm doing a lot of studies now with NSOs, nitrogen, sulfur, and oxygen compounds. I believe that's what gives the difficulty in the EOR because as you see, all the gluing material has sulfur compound. So what we are doing is we are more focusing on the H and the C and not so much on the NSO. The NSO is the building block for the asphaltene, is the building block for the mobility issues. It's also giving us a lot of aromatic. It's giving us the heaviness of the API and the gravity and the density of the crude oils. I think it's time now to look at the NSO and how we can marry the carbon and the sulfur. You see, with the NSO, the heavy dude, the heavy guy is the sulfur. Not to dismember the others, the nitrogen and the oxygen, because they all form aromatic compounds. But how well we know about these things? I think in the research sense, thinking outside the box, we need to look at the sulfur as a promising element that it can enhance recovery somehow, either by depleting it or reducing it, or even mixing it with the carbon or the other atoms. With that, I think that's my opinion about that. Yes,
thank you, Dr. Malik. Appreciate it. And this goes related to what Oscar, Oscar, are you around? As Oscar present us about how we can articulate these new materials, new perspective with nanoparticles, and as well how we can see and integrate the oxidation and reduction with the isothermal reactions conditions with the different materials considerations that we have it on this, as you say, NSO, sulfur conditions, how we can interact with them. So really, so we have a lot of opportunity to bring these new minerals, new conditions, new elements to the reactions and to the in situ conditions we have it. So we put together fines migration, ion exchange, saponification, mineral dissolutions, oxidation, reduction, isothermal conditions. Any feedback related to all our workshop, please welcome all of you. Yes, about what is your experience about the next steps that we are going to be looking forward, and how our emulsions and conditions we have in situ and in surface is on our challenge. We can come across and work on that one. So really would like to say thank you to all of you. Have been very successful. Thank you for all your comments, panelists, and thank you for all the efforts you put in to be on this journey today. Thank you, Sol, Nubia Solange Reyes, that help us to put together all these amazing panelists. Liz Balbuena, thank you very much. Adriana, Maria Rosa. I really would like to say thank you to all of you, and let's continue for our next steps that we are going to be together on September, and invite you to be with us on the next step that we're going to have low water salinity flooding that will be going on September, and there will be a virtual meeting like this one on Saturday. We will be together. That will be previous to our Australia meeting from the annual conference. So thank you for being here. The questions that are already have been into the chat that we didn't answer today, we will contact the speakers and we will send you the information. And please follow up. Welcome as well to be part of the volunteer teams. As we have been saying, we have the different task forces join us. We are going to deliver a report for our International Energy Agency, how EOR is part of the solution, how our technology collaboration program can integrate with hydrogen to greenhouse gas conditions, to improve oil and gas energy efficiency, to get energy for our communities. We are part of the solution. We are not isolated. And it's something that I really encourage you to bring as well, not only our professional aware to our students, that we are today working on this energy transition efficiency because we are part of that. We cannot feel excluded from this one. We have the knowledge to be part of here, and our competencies we will add. And welcome to share with us as well. Welcome to share with our community this fight. So thank you very much, all of you. Thank you, really, really appreciate it. Dr. Bernard, Dr. John Pantano, Khalid, Alisa, and all the speakers that we have today at this amazing journey. And see you next time. Thank you.
Okay. Thank you.
Cesar, please the share screen in the slide for the panelists. Thank you for your support and for your time.
Okay, thank you. Thanks a lot for the invitation.
Really, really a pleasure to have all of you here. Have a nice weekend and keep safe. We get already some shots of the vaccination, but keep the distance and the protocols will keep us safe too. So hopefully we can meet again on presence in any space on the world. Really would like to say thank you. Thank you, all of you.
Thank you.
Thank you.
Thank you, Cesar.
Thank you, Nora.
Thank you very much.
Thank you, everybody. Thank you very much.
Bye.
Thank you all.
Thank you very much.
Bye.
Thank you. Bye.
Thank you. Bye-bye.
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 Bye-bye. Thank you.